Yes, that's time. Okay. Okay. Good morning, everybody. Is it not? It's not loud enough.
That's the physics. Pull the mic forward.
And
this one, even to like.
Okay. All right. Let me do this.
That would be fine.
Thank you, Paul. All right. Can you guys hear me? Yes. Okay. I see a few thumbs in the back, maybe tentative. Okay. It is 10 a.m. And I want to welcome everybody to this year's NASA Hubble Fellowship Program Symposium. My name is Angelino, for the new fellows who don't know me yet. I am currently the Sagan lead for the Hubble Fellowship Program, and I am welcoming you because the Sagan part of this program is run out of the NASA Exoplanet Science Institute, which is located here on the Caltech campus. And so I'm doing a very quick hello. So I am Dawn. This is Paul Green, the Einstein lead, and Andy Furniture, the Hubble lead. Say hello.
Oh, sorry. Hey, everyone.
All right, and we're going to move things along as quickly as possible this morning so we can get to your amazing, awesome science. And so with that, I am happy to introduce NEXScI's Executive Director, Chaz Weichman, my former boss.
I work for her.
Actually, now that's true. So as some of you know, I was Deputy Director for NEXScI here under Chaz. Until the end of April, and then I moved to JPL. I am now the manager for NASA's entire exoplanet exploration program, and so I'm now his boss, which is really, really weird.
I always work for God.
So if any of you during the week want to talk about like huge transitions in jobs, come talk to me because I'm still trying to figure it out, but I'm happy to lend anybody any insight. All right, with that, I'm going to hand it over to Chaz.
Thanks, John. So just like to welcome you to Pasadena. As John mentioned, the NASA Exoplanet Science Institute has been running the Sagan side of things, the exoplanet side, originally the Sagan program, and now integrated into the NHFP. Do I have to do the slides?
Oh, yeah. There's a clicker and
So just a very quick word about NEXScI itself. In terms of these 5 pillars of things that we do for the community, there's the Sagan program, which is has 2 main parts. One is the NHFP part, which we're participating in today, but also the Sagan Summer Workshop, which I'll discuss in one more slide in a minute. But that's been going out and training early career scientists now for 25 years. We run the Exoplanet Archive, something called the ExoPop, which takes data from the referee literature, counts up the 5,000 plus planets that are currently in the referee literature, all the properties of the planets you can glean from that, but then also the exobox, the sandbox, or anybody can add in their own spectra images and so on, sort of Facebook for exoplanets. We run a bunch of long-term archives for various missions going back to LBTI, we're looking forward to things like Cube and Pandora, and small sats. We run the tech operations and the tech archive for NASA's 90 nights a year. Those of you who did the tech proposal, which we'll do a few days ago, they are going out for review and we'll let you know on December 1st. We also are in charge of helping NEXScI run what's called the NHFP program, which is basically spectroscopy and high resolution imaging on a variety of telescopes to really help in the characterization of exoplanets. One word on the next STScI workshop. It will be the demographics of exoplanets and also the demographics of all the people that are attending exoplanet workshops for the last 25 years. And the whole point of the demographics is to have each of the different techniques that come forward and produce data and contribute to the demographics puzzle to help learn what those different applications have produced, but then also how to integrate all those to find out that you're actually looking at an exoplanetary system and what the demographics of those really are. And each one of these systems has their own biases that have to be worked through. The other thing I'll mention in the slide or two is that NEXScI is embedded within a larger organization here on campus called IPAC. And George Liu is the director of that. He's sitting somewhere back there. And IPAC covers a whole range of mission sizes and wavelengths. It started out as an infrared processing center, but basically we run all sorts of different missions. This is just a list of some of the active ones, present and future. In the past, of course, we've done things like Herschel, Planck, Spitzer Science Center. It's a very active time now for IPAC, where we basically have a launch of a mission that we're responsible for every year. So NEO-wise, there's Euclid now started to take data, Lunar Trailblazer, I think launching January 1st. Is that the right date, George? Small set going to the moon. SphereX will be a very exciting sky survey to basically give you a spectrum of every WISE object in the sky. Roman, a key part of working with Space Telescope and Goddard on getting ready for Roman, including the coronagraph and a lot of microlensing work. NEO Surveyor will find any asteroids that are going to come and hit the Earth, hopefully before they hit the Earth. Ariel, which is an exoplanet mission, joint with ESA, and then a recently selected UV survey telescope. Lots of different archives, some of which people will know from their different activities. The ERSA archive is all anything infrared for many, many years, and that's extragalactic database, the various exoplanet archives, the tech archive. People doing condomin probably know about ZTF and PTF and various outreach activities. So as mentioned briefly, IPAC is very science driven. We have a very close coordination between the scientists and the engineers. There's lots of postdocs. We have sort of a staff of very experienced scientists, but also then younger scientists coming on board, and the scientists all play key roles in the projects they participate in. And with that, I will turn it over to Dawn with only 30 seconds over, Dawn. Give me a break.
Good job. Thanks, guys. Okay, we are trying to make sure that everybody in the back can hear with the microphones. So if you can't, like, just wave your hand.
Let me say one thing.
Oh, one more, of course.
Yes,
Okay.
One thing we had, we look back at the slides I had that showed all the different missions. If any of you are actually interested in finding out more about what Roman is doing, what Euclid is doing, what SphereX will do, Megan is going to put together. This is Megan. She runs everything. Megan is awesome. She'll put together a Google sign-up sheet. So during the week, maybe Wednesday afternoon, before, during, after the JPL tour, if you're interested in finding out about any of the specific missions in a bit more detail, what the data are like, when they're going to be available, and so on. If you sign up on the sheet, we'll arrange to get some IPAC scientists together to be able to talk to you.
All right. Okay, and so next I would like to introduce Nino Cucciara.
Yeah,
Right?
that's good.
He is our program scientist at NASA headquarters.
Thank you so much. Can everybody hear me? Okay, good. I'm Italian, so I tend to speak a lot and talk to my hands. So I held my phone and wrote something down, so I stick to the time, all right? So yes, I'm Nino Cucciara. I'm the program scientist in charge of the NASA Hubble Fellowship Program for headquarters. And I can tell you on behalf of myself, NASA headquarters, my deputy IPAC NEXScI and the Hubble Project, I see Jennifer Wiseman is here, and the IPAC. We are absolutely thrilled and proud of you all for being here, for the science that you have already done, and we're really looking forward for what you will do. You've been selected among the brightest early career scientists in the world. And we really can't wait for this week and for whatever come after. I just want to mention that the NHFP and the program does not only support excellence in research or research leader, we also support inclusive leaders. And what we mean with that, we know you're going to be the leaders in your field and subfield, but we entrust you and NASA entrusts you to really understand the community, the people that work with you, you care. We know that you care about the others, and we hope, we believe that you will be able to create a safe and inclusive working environment wherever you're going to be in your endeavors. And this is very important for NASA. It's very important for us because you really are the forefront, the early career scientists. They're going to be advisors, faculty, mentors of future generation of astronomers. And as the Astro 2020 Decadal Survey says, we cannot disentangle the science that we do from the people that do the science. And I think this is very important for us, and we really want you to, NASA really want this to be the future of our generation of astronomers in our field, both inside the United States and outside. So really create a new generation of leaders. And if anything, I'll be here for a couple of days, 3 days or so, because I have to be back home for other business trips. But looking forward to talk to all of you. Email me, talk to me. I'm really looking forward to know you more on the personal level as I learn from your research level in the next few days. And I have 2 minutes and 50 seconds extra for you to talk about science. Thanks a lot.
Okay, I think the podium mic works better than this one, but I'm going to stick with this one while Kevin brings up the slides for the leads. It's really bright. While he's doing that, there's a few logistical announcements. One, the restrooms in this building, if you go out this door, take a left, and then take a left, they will be on your right. And the food that well, the food this morning, some of it's out here and some of it was outside. I think tomorrow Frank said that he's going to have it all right here, but all the seating is still back there. Yeah, we need to go to the first slide. So we will be eating outside on the patio, or you can gather out here and eat here as well. Unfortunately, they do not allow. This is not my room, not our room. They do not allow food or drinks in this room other than water and closed bottles. So please be respectful of that. We don't want to have to ask you to go dump your coffee or whatever. So please remember that. There is Wi-Fi, that we have Eduroam here, but we also have the Caltech visitor account set up, and that's for folks who don't have Eduroam. And it was on the screen when you all walked in, but it's also up here on the board behind me. And then finally, because I don't think it's in our slides, there'll be a group photo at the start of lunch today. And so don't take off at lunch, that and we are supplying lunch, so you shouldn't take off anyway. We should use this as an opportunity to talk to each other and talk to us if you have questions. Okay, so with that, I am going to kick off the slides and I'm going to do the first few and then Paul and Andy will also get up and do some. So welcome. Okay, this is our 6th NHFP Symposium. And it's the first time that we've been here in Pasadena. We've been rotating between the 3 centers. Next year, we'll be back in Baltimore at Space Telescope. I'm happy to say we have about 60 of you giving science talks, and then we have a whole bunch of non-science sessions as well. Your SOC, who we'll get to in a minute, decided that these were kind of the top priority non-science things that would benefit all of you the most. So we have tomorrow morning, we have a session on community collaboration in academia. We have our dinner tomorrow night, which will be outside on campus. It's a taco bar, but we will have drinks as well, both alcoholic and non-alcoholic. Wednesday morning, we have a career panel. Wednesday afternoon is free, unless you signed up for the JPL tour, which I'm going to take too, because even though my new job is at JPL, they have hiring freeze. I did not get there's no orientation. I did not get a tour or anything, so I'm going to take it all with you. And so for that, you need to have your ID with you. If you are a US citizen, your driver's license will work. If you're not a US citizen, you have to have a valid passport with you or green card. They will not let you in if you do not have one of those things. So please remember, everybody, bring your ID with you on Wednesday. Okay, and then Thursday we have our session with the benefits folks, the grants folks at Space Telescope. This is really where you get to ask your questions and ask for things that you're either unclear on or that you don't that you wish could be a thing. And then most importantly, Thursday night, you have to come to open mic. Last year it was just spectacular. It will be in this room. Yes, in this room. I'm looking at Megan. She helped put all of this together. In this room, we will have snacks and drinks that we'll do out on the patio beforehand because we can't have snacks and drinks in here. And it is so much fun. You guys are so talented. It's amazing. So please come to that. I know it's an evening thing. It's the first time we're trying it in the evening. The SOC thought it could work. So please do come. It's a lot of fun. Okay, so distinguished guests, you've already heard from Chaz, and you've already heard from Nino. Mark Knappen is going to talk to us remotely tomorrow, I believe, and Jennifer Lutz you'll hear from after the first science session today. And so I think it's 11:45 or something. Also, I know Nino already pointed out, but Jennifer Wiseman, the senior project scientist for the Hubble Space Telescope. And Jennifer, you want to say a few words?
Yeah, so thank you. I just wanted to welcome you also. I work at the NASA Goddard Space Flight Center in Maryland. And as the senior project scientist for the Hubble Space Telescope mission, Hubble in Heritage has been the sort of portal for the Hubble Fellows program. So we still fund it through the Hubble project and through our contract. We oversee, we work with Nino and the leads on the policies of the program. We hear from you what policies might need to be changed and so forth, and we appreciate that. But now, of course, as you know, the programs merged, the Hubble and Sagan and the Einstein Fellows, and we're delighted about that, but we still are the kind of heritage portal for funding and overseeing the program. So I'm here to see your terrific science, but I'm also here to listen to your vision for the future of the field and this program. And so I look forward to talking with you over meals and things. And finally, I just wanted to say that I am a former Hubble fellow 25 years ago and had a career that encompassed both research and science policy management and mission oversight. So if you want to talk to me over meals and things about career possibilities after your fellowship, I'm very happy to have those conversations. So welcome.
Thanks, Jennifer. Okay, we have a whole team of people that helps to run this program. You've met the three leads. Megan, I can't say enough, how much Megan has helped this program, especially in the last 4 or 5 months when I have been, off doing another job at JPL. I told everybody that I was committed to being the Sagan lead until NEXScI found my replacement, which they're close to doing, but haven't done yet. So I will be helping out with the transition to the new person as well. So don't despair. You can still come to me and ask me questions. But anyway, I'm still the Sagan lead, but Megan has picked up a lot of slack, that all the balls that I've been dropping. Everybody owes Megan a debt of gratitude. So I think, can we all give her a hand? And she hates attention, and her face is part of it. Okay, so, sorry. Okay, but we also have, other folks that are helping, with this symposium as well. Frank, and Nancy, actually, you saw out at the table this morning. Frank will be with us all week. Kevin, Paget, who will be here, he's hiding behind the column, but you'll see him pop up. He's helping us with the talk transition. And, Sharita at Space Telescope, who is part of the events planning team there, and she's been helping us also from the other side of the country. And then, of course, we have your SSD. So everybody should, those of you on the SSD, if you could stand up so people can see who you are, please. And the SSU is always made up of fellows because this is your symposium, not our symposium. It's your symposium. We want you to get out of it what you want to get out of it. And so we're really happy that every year we have a number of fellows who do volunteer to help with this. So thank you very much to all of them. Okay, this is my last slide, and then somebody else is coming up. But code of conduct. All right. I don't think we really need to go into this with this group, with all of you. As Nino said, you're chosen not just because you are scientifically impactful and amazing and awesome in your field, but because you're good people. You're inclusive. And so this is just here to remind everybody, that we want this to be a safe space. We want everybody to be able to be free to come up with crazy ideas and not feel like you're going to be harassed in any way, shape, or form. Just be be good humans, be decent humans. If something does happen and you're upset or whatnot, you can come talk to any of the leads. You can come talk to me, to Paul, to Andy, and we will deal with it. Okay, we're very serious about this, of course. Okay, who's coming up? Okay, and here is Paul Green.
Okay. Hi, everybody. Welcome, good morning, and all that. This is always an exciting week for me because I love to hear the breadth of science, and as I was saying at breakfast, I'm always amazed at also the talent in the room when it comes to actually the quality of the presentations and the pedagogy. I'm not sure why, because that's not on the application, but it's always very impressive. For the presentations, you've heard most of this before, I think. Please upload your slides at the link that we sent around in the email a day before. I note that there are some presentations that are still not there for this afternoon. Please upload things so we make sure everything runs smoothly. So remote speakers, if you have any concerns about the quality of your connection, it would be good to submit a video of the talk that we could just play. As you know, the length of the presentation is 12 minutes, and then 3 minutes for questions and transition. So just really a couple of minutes for questions. But of course, you're all here all week, so you can ask each other questions all week long at our various opportunities for social interaction, of which there are many. If you're presenting remotely, please mute your mic. If you're not speaking, if the connection is spotty, you can again upload a video, or we can advance the slides for you. And remote fellows ask questions by typing into the Zoom chat, and the public can ask questions as well for those who are watching the YouTube stream by typing into the YouTube comments. So after a talk is over, you guys can use Slack for any further discussion, so that can get interesting. And the science talks will be recorded, but let us know if for some reason you don't want your talk to be posted publicly. So the open mic, which is my favorite thing, will be the presentations, or whatever you call them, the performances, whatever it is, it'll start at 8:30, although we'll gather here for drinks and snacks at 8 p.m. on Thursday evening. This can really be anything. It can be recipes, it could be poetry, it could be interpretive dancing, it could be ballet, it could be music, etc. We had a great rap last year. And so I definitely encourage people to sign up. We will have a piano, we will have an acoustic guitar, and a nose flute if you need it. We'll just ask. But it's a maximum of 10 minutes. And yeah, you can sign up on the Google Sheet. There's a link in the Slack, and the link went around by email, or you can just email us with your suggested presentation. Should be a lot of fun. And Andy is up next.
And really, you sign up for the open mic, or else all perform.
That's right.
Yeah, it's actually you might want that, so you might want to. Yeah, yeah, right. Yes, but yeah, it's actually, you could not tell us at the last minute, and then, oh, we'll have to perform. But okay. So let's good. Yes. Wait, oh, you've already done the runners. Yeah, I'm trying to, was it?
That's one.
Does it only go forward?
The one underneath it.
Oh, one of the E-head. I mean, it's not directional. Yeah, I put that, but there you go. Yeah, one more. All right, I'm on top. All right. So today, this evening, there's a stroke. Actually, that's the next slide, right? So, oh no, it's there. So, right, this evening, there's astronomy on tap at two of our fellows, Ekta and Rohan, are speaking. So, go and enjoy that if you would like. It's you're all going to have to be in the doghouse. So this is it. All right. But as we've already heard, we're going to have a group photo today just before lunch. And the symposium dinner is, oh, sorry, right. Yeah, Monday for lunch. It says Tuesday, but it's Monday.
Yeah, it's today. Your photo's today.
Yeah, don't pay me attention to it. Symposium dinner is tomorrow. That part, that's right? Yeah, okay. Symposium dinner is tomorrow. And that will be the 80 photo. We've got a map up that'll come up next to show you where that is. It's closer to the hotel than this is. Wednesday is the afternoon again, is free if you're not going to JPL. If you're going to JPL again, bring your ID. And that's optional. There are lots of fun things to do around here. We're a bit far from Disneyland, but yeah, there are lots of other things we can do. And then again, Thursday is open mic. All right. So here's this. Yeah. Oh wow, that's big. So we're down here. The hotel is about here-ish. Well, actually, it won't go that far. Oh, I see, because Oh, this is clever.
Yes, it's so the folks at home.
Yeah, it's not only, yeah, okay, it's got a gyro or something. The world is just so advanced. That's amazing. All right, and so Avery House is up here. Yeah, yesterday I tracked my luggage for the first time and I could see it was on the plane with me.
That's great.
Yeah, I know. It was great, actually. All right. Okay. COVID protocols if you want. We have masks if you'd like. There are some free masks. Take one home. Several COVID kits are available if you feel, scratchy the throat or anything like that. You get a COVID test, and we recommend you do that if you don't feel well and if you don't want. It's highly contagious, so not so dangerous anymore, but I felt leadership, that's why I wear the mask. And questions? Any, yes, Jennifer, you're supposed to answer the question.
Yeah, I know. But for the tour of JPL, is the transportation leaving from here or from the hotel?
From here, from
So
here.
people need to
Yeah,
start
actually,
their
it
laptops.
has to be very quick for that. So in fact, we're gonna have to give you, there'll be box lunches there.
Okay.
So it's gonna be we have like 15 minutes to finish after the session to get on the bus.
You can take the food on the bus with you if needed.
Okay.
Yes. Yeah.
Okay, great. Okay, I think then let's get started.
Okay. Okay, oh yeah, and then also for the JPL tour, there is a small gift shop in the visitor center. And so the main visitor center, or sorry, the main gift shop will not be open after the tour ends. And so we're going a little bit early, so folks can, if you want, you can get stuff at the smaller gift shop. Okay, so now we're gonna move into the science. So Cassie is going to be our first chair. And so a reminder that the timer, there's a timer sitting here. It will turn yellow when you have 2 minutes left, and it'll turn red when you have 1 minute left. And then when the whole screen turns red, it's time for your questions. So please don't go over or you will not get any questions. I know everybody loves answering questions, so. Okay, with that, and then you can use either that mic or this one, it's up to you, but I'm gonna hand this one to Cassie so she can introduce.
Okay, hi everyone, welcome to the first science session. My name is Cassie Lockus. I'm a Hubble Fellow at the Harvard and Smithsonian CFA. So first we are going to hear from Andre. And so the timer is right here. If you aren't looking at it, I'll sort of wave at you when you have 2 minutes left, but go ahead and take it away.
Can I help you?
Yes.
All right, thank you very much. So I'd like to start by thanking the organizers, the NHFP leads, and everyone who's involved in making the program happen. So thanks for bringing everyone together, and I'm looking forward to all of the talks for the rest of the week. So in the short time that I have, I'd like to tell you about DESI, and particularly about the analysis that I spent all of 2023 and the first half of 2024 working on. This is the analysis of the first year of data. I'll tell you a little bit about the instrument and then the analysis process, and in the end, I'll also present a few of the results. So what's DESI? DESI, or the Dark Energy Spectroscopic Instrument, is the first stage 4 dark energy experiment. It started in 2021, and it's a spectroscopic survey. This means that we're taking spectra from loads and loads of extragalactic objects. In order to do this, we have an army of 5,000 robots. Each of those carries one fiber that collects the light from one galaxy. And then all of those fibers feed into 10 spectrographs that actually measure the spectra that we'll then use. And in order to do the survey that we want to do, DESI was optimized to take 5,000 spectra every 15 minutes, which is really, really impressive. So that means that for every observation, we have to repoint the telescope. And then each of these robots, I'm not sure if the video works. Oops. I guess the video doesn't work. So you have to imagine that each of these robots actually moves around. So between each observation, we have about 1.5 minutes to point the telescope to a new position, and then move each of these little fibers to the position where we know the light from a galaxy will be coming down. And all of this is to build the largest 3D map of the universe. And to do the objects that we're looking at, there's a few different types. So at low redshift, we have these bright galaxies that are observed when the moon is up and close to dusk and dawn. And then going up in redshift, we have luminous red galaxies. Even further, we have emission line galaxies all the way to redshift 1.8. And then finally, the furthest redshifts, we have quasars that are observed between redshift roughly 0.8 all the way to redshift 4. And above redshift 2, we have Lyman alpha forests, which is what I'm mostly going to be focusing on today. DESI is a huge collaboration, though, and I think we just passed about 1,000 people. So I really cannot do justice in 12 minutes to the breadth of science and the amount of results that we have with just this first year of data. Now, luckily, there's another DESI member in the room who will be giving the talk at the end of this session, and he'll be telling you more about the galaxy clustering side of this. So with this first year of data, the first results that we had came out, and here we're focusing on baryon acoustic oscillations. So these oscillations formed in the primordial plasma and were left as an imprint in the matter distribution in the universe after recombination. And the cool thing with BAO is that because they were left as an imprint after recombination, they were free to evolve with the universe since redshift 1000. This means that we can use them as a standard ruler to track the cosmic expansion history. And because DESI measures the large-scale structure in 3 dimensions, that means we can measure BAO both across the line of sight. So that means the angle that this feature has on the sky, and also along the line of sight. And this is sensitive to the local expansion history where we make the measurement. So BAO analyses are fairly simple as in the big picture of cosmology. All we care about is this parameter that I'm showing here. So what we do is we have some reference cosmology, we call it the fiducial cosmology, and all we want to do is essentially fit this feature. We have 2 ways of doing this, either along and across the line of sight with these parameters at the top, or you can have a different parameterization where you're instead fitting for the isotropic BAO scale and then for the anisotropy separately as well. And this is also known as the Alpha-Paczynski effect. So as I said, I'll mostly be focusing on the Lyman alpha forest. And for this, instead of actually using the galaxy positions themselves, instead of building a 3D map of galaxies, we use the absorption from intervening neutral hydrogen in the universe, which is present in all the spectra to high redshift quasars. And this means that instead of having a discrete map with galaxy positions, we instead have a continuous map along each line of sight that tracks the large-scale structure in the universe. And in order to measure this BAO feature, we just compute the correlation between different absorption values from different spectra. And this looks something like this. And what we care about is this feature that appears at around 100 megaparsecs divided by h. And this is the BAO feature. So a BAO measurement just means we're measuring at what scale this feature appears. Now, beyond just the Lyman alpha, we can also cross-correlate the absorption with the quasar positions themselves. And this gives you the Lyman alpha quasar cross-correlation. And this is another probe that we can use to, again, you can see the BAO feature and gives us the same measurement. So a lot of my time last year was spent on making mocks. So a big part of this large cosmological survey is making sure that they're thoroughly validated. So this means we spend a lot of time making sure that we can simulate our entire instrument, our entire data collection process, the noise, all of the astrophysical contaminants, and everything that's present there in order to be able to make sure that our results are robust. So here I'm just showing a few constraints from those large set of mocks. basically showing that we are able to recover 1, here for these parameters, which means that the cosmology results that we recover are unbiased. We also had a large number of variations, and here I'm only focusing on the Lyman alpha forest. There's a whole other set for the galaxy clustering. So here you're going to each step of the analysis and trying different variations and making sure that your final result is robust to all of those changes in the analysis. So this was us for essentially an entire year. One special part of this analysis was that everything was blinded. So we didn't actually know the result. We had to make all of the important decisions in the analysis without knowing the result. And then in December 2023, we had a Zoom meeting with a few of the key members of the analysis where we unblinded. So this was on December 8, 2023. It was a very, very exciting day. After a year of work, we could finally look at our results. So this was the picture that we knew before. In blue, I'm showing the previous state-of-the-art result for high redshift cosmic expansion history constraints. That's from the Sloan Digital Sky Survey. And then in red, we're showing our blinded measurement. Now, this is all referenced with respect to some reference cosmology, in this case, Planck. So Planck is somewhere here at 1. So we knew that our blinded result is quite in tension with Planck. Now, that could be because of the blinding or because we found some new physics. And it turns out it's consistent with Planck, which means consistent with lambda CDM. That was a really exciting day and a lot of pressure to get all of that result, but in the end, everything worked out. So now let me quickly go in the last few minutes over the full results from DESI, including galaxy clustering as well. So I'll show a few of these slides. On the left, it's the actual measurements that we make. At the top shows the isotropic BO constraint with respect to our best fit. And then the bottom shows the anisotropy, that's also known as the Alpha-Paczynski effect. Now you can see that the first point, we only have the isotropic measurement from bright galaxies. And if you translate this measurement in flat lambda CDM, that corresponds to constraint in this plane over here. So you have the matter density and then this degenerate combination of the Hubble constant and the co-moving scale of BAO. So you see you get this full degeneracy. Now moving forward in redshift, we have 2 bins from luminous red galaxies. And now we also have the Alpha-Paczynski constraints here as well, which means we can break the degeneracy and you get this constraint in red. And you see that as I go forward in redshift, you get more and more constraints and the angle of this degeneracy changes, right? And when I get all the way to Lyman alpha, you see it approaches this 45-degree angle here. And this is truly where the power of DESI comes in. We're mapping this BO feature across most of the expansion history of the universe. And really the power in the cosmological constraints comes from combining the low redshift measurements with the high redshift measurements. So you can think of it as the intersection between this red and green measurement at low redshift with the Lyman alpha measurement at high redshift. That's really where the power of DESI comes from. And of course, the final result, you can see it right there. So quickly going through some of the highlights. We have constraints of the Hubble constant, of course. Now, the sad part is BO doesn't directly measure this because we have this degeneracy here. So we have to use data from Big Bang nucleosynthesis. That's a prior on the baryon density. And that allows us to break the degeneracy and get a constraint on the Hubble constant. You can see it here that it's consistent with the CMB and in quite a bit of tension with the Cepheid analysis from Schuss. And then we also had a look, of course, at the dark energy equation of state. It's in the name of the collaboration. So here we're working with a case where the equation of state of dark energy is a constant with time, and you can see the constraint from DESI. And really here you can see the power of DESI when I compare it with other constraints. So that's DESI, and now I'm adding the CMB results from Planck. And you can see that if you have Planck, you have quite a degenerate combination here. So you're not able with just Planck to constrain this equation of state of dark energy. And I also add now 3 different measurements from supernovae 1A. And you can see with supernovae, you also have quite a big degeneracy. It's just in another direction. So this really shows that DESI as an instrument can really get alone a pretty good constraint on the equation of state. Now, of course, when you're doing cosmology, in the end, you want to combine everything. And here you can see the orange contour showing the combination of everything else. And that is consistent with the cosmological constant. Now, this is my last slide. As I said, DESI has a lot of science. So I quickly want to just say that we also measure curvature, and it's consistent with the universe being flat. We have some of the tightest constraints on the neutrino mass to date. And then, of course, the big news is that when we consider models with evolving dark energy, and we combine all of these probes, so in particular, the DESI BO measurements with cosmic microwave background, and then with one of these 3 supernovae data sets, we start to see some hints that dark energy might be evolving. And these hints vary between 2.5 sigma and 3.9 sigma. So I leave my last slide up, and the last thing I want to say is that this is just the beginning. This is only the first year of DESI data. We already finished collecting the year 3 data set in March this year, and we're currently working on the analysis. We're still in that blind phase right now, so I don't know the answer, and we have to decide on all of the steps of the analysis before we unblind. Thank you.
Okay, questions? Yeah, in the back.
I study planets, so I'm sorry that for this very naive question. But in planetary science, the equation of state is basically like for a material on the planet, how the density changes as a function of pressure and temperature. So what is the equation of state of dark energy in the universe?
So it's exactly the same. So it's the relation between the pressure and the density. So the relation between
the pressure, the expansion.
Oh, can you hear me?
Yes.
Right, yeah, so it's the relation between the pressure and the density of this dark energy. And then, so the trick is that when we use this type of parametrization, well, there's different parametrizations, and there's many different types of models for this. So when we use this type of parametrization, we're just, the main point is to test for deviations from a cosmological constant, where the equation of state is equal to -1 and doesn't evolve, right? And then there's a different question of, if you find deviations, which one of many, many theory models that have been developed over the last 25 years can actually explain those deviations? Right, so this is just a simple parametrization just to quantify departures from a cosmological constant.
Thank you.
We have our next speaker come up, please. And maybe if there's one more really quick question. Yeah.
What caused the tension with STSS DR16, the plot you showed?
Can you repeat the question? Just so the folks online can hear.
Right.
So what caused the tension with SDSS? You mean, sorry, here.
Yeah. Why was STSS offset?
Right, there's no tension here. So with our blinded result, maybe, but our actual result is this red one here, and this is consistent with the statistical fluctuation.
It's 3 sigma?
No, this is less than 2. The intersection. You have to think about the intersection in the full 2-dimensional plane. So, and also something else to note is that we do have some data in common with SDSS, about 10%. So there is a little bit of correlation between the two. But we actually looked at the tension, and it's under 2 sigma. There's no tension here. There are more interesting ones in the galaxy still.
Okay, I think we should move on. Let's thank Andre again. Okay, next up we have Haley, who is going to be talking about the low redshift distance redshift relation beyond FLRW, which I hope you will explain what that is.
I will, don't worry, I'll go through it all. Awesome, thank you so much. Hi everyone, my name's Haley. I'm an Einstein at UChicago. Oh shit. Sorry, getting off to a good start. Yes, I'm an Einstein at UChicago, and I'm excited to talk to you today about one of my kind of areas of interest in my research. And I hope that I'll just be able to give you a bit of a background on that research area, which I've been working on for a few years before my fellowship, during, and hopefully a little bit in my last year coming up too. So in cosmology, one of the things we're really interested in figuring out is how the universe is expanding. I did that on purpose. Finding out how the universe is expanding, and we use a bunch of different cosmological observations to figure this out. And essentially, most of our cosmological observations have converged on telling us that our standard model does a pretty good job of providing an explanation for all of these. And the pointer.
Just hold it down. It's Bluetooth.
Oh, gotcha. Oh, okay, there's a lag. Okay, so our standard model does a pretty good job. And this is the flat lamp cold dark matter model based on Einstein's theory of general relativity. And well, it does a really good job of explaining most of our cosmological observations. The interesting thing about it, in my opinion, is that in recent years, as our observations get more precise, we're starting to see some cracks come about in this model. Some of our observations don't match the specific predictions of this model. And of course, the most notable of these is the Hubble tension. I won't go into a lot of detail about this, but this is essentially just a disagreement between two different ways that we have to infer how the universe is expanding at redshift 0, or this Hubble constant H0. Essentially, our early, oh my gosh, how are you guys pointing with this? The early universe and the late universe disagree with one another. This is not the only tension between our observations and lambda CDM. There are a few others which I won't go into. And of course, there is this 95% of the energy density of the universe that we don't quite yet understand. And so there are cosmologists of all types who are interested in trying to figure out these puzzles. I'm one of them, and people do this in a variety of different ways. The one that I'm most interested in is this one down the bottom, which involves considering existing physics that we know is there, but is neglected or overlooked in the simplifying assumptions underlying this model. In particular, I said that cosmology is based on Einstein's theory of general relativity. What this means is that the dynamics of space-time are governed by Einstein's field equations here, where the left-hand side tells us about the curvature of space-time, and the right-hand side tells us about the matter content in mu. These equations might look pretty simple to you, but I assure you they are not. This is a highly complex nonlinear system of equations. And so in many areas of physics, and cosmology is no different, what we typically do is make some kind of simplifying approximations to make this a lot easier to deal with. And this typically involves some kind of space-time symmetry. And in cosmology, the assumptions that we make are those of homogeneity and isotropy, or that things are the same everywhere and they look the same in all directions. Now, this can either be exact homogeneity and isotropy, and this gives us the FLRW, or free-formation Walker class of models, or they can be statistical homogeneity and statistical isotropy. These are different things. This is another branch of my research, is figuring out whether these two actually give us consistent results. Okay, that was my elapsed time. It's remaining time. Good. Okay. So the universe is homogeneous and isotropic. What we can do is we can take galaxy surveys like this one on the left-hand side, put galaxies on our redshift or position and position, XYZ position diagram, and we can just measure at what point this distribution of galaxies becomes homogeneous, like a Woodland scale. And when we do that, we get something like 100 to 300 megaparsec, depending on what kind of measure that we use for homogeneity. This is what we call as the homogeneity scale. This is an extremely important scale in cosmology because it serves as a key motivator for when we believe that the use of the FLRW models is a good description of the dynamics of the universe on large scales. Whether this is true is another aspect of my research, but the thing I want to talk about today is the fact that we do have cosmological observations that occur near or at or even below the scale of homogeneity, which implicitly assume and impose the FLRW models or some other simplified description of the geometry of spacetime. And my interest in this field can be summed up at this last point here: is this okay? Is this an alright? Is it okay to impose these FLRW models so close to this homogeneity scale? And in particular, I'm going to talk about supernovae and implications for the Hubble constant. So this is a plot of some distances and redshifts of Type 1a supernovae. We can just measure this apparent magnitude in redshift, put them on this diagram, and they fall nicely on this line, which is good, tells us the universe is expanding. But if we actually want to extract any kind of cosmological information from this line, we need to parameterize it. And usually that's where the FLRW models come into our analysis. And so when we're talking about these kind of low redshift observations, so the local measurements of the Hubble parameter go up to about 0.15. here. And when we're talking about this really low redshift regime, it's typical to use a technique called cosmography. And so this involves a Taylor series expansion of the luminosity distance, which is related to the y-axis in the plot before, as a function of redshift, typically truncated at third order. And when we do this, we can write the coefficients of this expansion in terms of these familiar cosmological parameters, the Hubble, deceleration, jerk, and curvature. And these parameters are mostly related to time derivatives of this function A, which is the scale factor in our FLRW universe. Scale factor tells us what length scales are doing as a function of time. So the first time derivative tells us how the universe is expanding. Second time derivative tells us how length scales are accelerating in the universe. I don't really know about the third derivative, but the curvature is very simply related to this constant K, which describes the scalar curvature of three-dimensional spatial sections in our four-dimensional universe. So the beauty of this kind of framework is that in deriving this, we haven't need to make any assumptions about what this function A of t looks like. So we haven't assumed Einstein's equations and we haven't assumed 70% dark energy. So this is typically referred to as being model independent. I'm doing this because it's model independent within the scope of the FLRW models, because we have explicitly assumed a particular geometry of the universe here. But if we're talking about these low redshift measurements, then inhomogeneities distort their underlying spacetime and change the relation between distance and redshift. And the question is this deviation from this FLRW relation significant for our current measurements, or only when we reach a really high precision, or do we just not care at all? And to look into this, we need to drop this assumption of the FLRW metric and go to a fully relativistic treatment. But luckily, I have a very clever collaborator, Asta Heinzen, who she derived this distance redshift cosmography, dropping the assumption of the FLRW metric. So you didn't have to do it. It looks like this. Look at Asta's paper if you're interested. Basically, we have the same luminosity distance relation as a function of redshift, but now you can see that these coefficients are instead written in terms of these kind of curvy parameters. These curvy parameters are the effective Hubble, effective deceleration, effective curvature, and effective jerk. They're called effective because they sit in the same place in the series expansion as their namesakes, but the physical interpretation of these parameters is not so simple once we leave the safety of the FLRW model. I'm going to explain that a little bit with an example. So I'm not going to really go into detail about the actual form of these parameters, by the way. You can ask me if you want to, but I just kind of want to get the main point across and that these parameters are different. So if we flash back to our FLRW parameters, I'm just going to use the deceleration parameter as an example. I noted that there was this very simple relation between Q and the second derivative of the scale factor, so how length scales in our FLRW universe are accelerating. So we can pretty definitively say that if we measure a negative value of Q, we have a positive value of A double dot, and thus our FLRW universe is accelerating. However, we lose this very simple geometric interpretation as soon as we account the effects of inhomogeneity and anisotropy. And you can't see it so clearly in this breakdown here, but I'll trust me for now. But essentially, when we account for these effects of inhomogeneity and anisotropy, observers can actually measure a negative value of Q without any kind of global acceleration of length scales in that universe. So this is just to say that having inhomogeneities kind of muddies the waters in what we're actually measuring with these objects. We can say the same thing about the other parameters. And a good way to see this is by doing what we can do, which Asta showed in her really nice paper, is to do a multiple series expansion of each of these effective parameters. Well, the parameter we're expanding it is this direction of observation. This is the vector telling us like where our supernova is, for example. So if you write down each of these parameters, this is the effective Hubble parameter, to kind of directly see the impact of inhomogeneity and anisotropy on these parameters. Now we have this first term here, which is our monopole term, doesn't care about which direction we look. And this is just kind of our inhomogeneous generalization of the Hubble parameter. So this is a larger expansion for our observer who's sitting in void, or a lower expansion if they're sitting in an overdense region. This term has been studied to death in terms of the Hubble tension, and it doesn't solve it. But we have another term here. So this term is a quadrupole, and it does care about the direction that we look on the sky. It cares about the C nu. And this term is not so commonly studied when we're looking at the impact of inhomogeneity on our low redshift cosmological measurements. So obviously this is something that I'm interested in. You can also do this for all the other parameters, but it gets a lot more complicated at higher order. So just look at Axis paper if you want to see. And so then the natural thing I wanted to ask is whether this additional term and similar terms of inhomogeneity and anisotropy in these parameters can impact our low redshift measurements where we assume that these terms are zero. And the most natural first application is the Hubble tension. So I've looked at this in a few papers over the last several years, and unfortunately the answer is probably not. So it doesn't seem like these kind of effects can provide a sole description for the Hubble tension, but that doesn't mean it's totally negligible. And some of the effects that we find are actually above the levels of current error in our measurements in the Hubble tension, and almost certainly for our future surveys as well. Cool, so I've spent my last 30 seconds just saying that we can ask a few questions, especially about the Hubble parameter. So this first term here I mentioned is a monopole term, so that just changes that kind of absolute value of the Hubble parameter. But this term cares about the direction we look. And so if we look at what the Hubble parameter looks like for one kind of example observer living in a universe, this is what they would see. If they could actually figure out what the expansion was in every direction of their sky, they would see this quadrupolar signal. And it gives you about a few percent variance. And so a few questions you can ask. One of them is, what if we have more objects preferentially in a certain direction, but we assume this quadrupole is not there? That's going to bias our kind of isotropic measurement of the Hubble parameter. Another question we can ask is, can we just constrain this quadrupole using our current data? And I'm going to finish by saying that this is what a student, when I was at Cambridge, Jeff Scal, did during our part 3, was to use the Pantheon data to try and just constrain this quadrupole. And the answer is that kind of. So this star represents a universe with 0 quadrupole, and this these are the eigenvalues of that quadrupole. I'm rushing here, I'm really sorry, you can ask the questions if you want. But the point is that 2 sigma, we can kind of measure this quadrupole, and we predict that with surveys like CTF, we have it detected at 5 sigma. Skip that, and I'm just going to wrap it up. Thank you so much.
Okay, do we have any questions? Maybe one quick question while the next speaker comes on up.
Can you do a match between your effective parameters and models that we know that are isotropic and so like the Yankee model, the second model? I think you can do that match to see which of those models you might be favoring or the same model.
You can do that. So I mean, the Yankee models are kind of talking more about a large scale kind of global anisotropy. And this is really just an anisotropy due to local structure. So this exists in the lambda CDM universe. It's just about whether the point at which we say, all right, now you can go to FLRW versus below that you can't, whether there is some kind of period in between where these are going to be impacting our measurements. So yeah, it's kind of a different effect, but yeah, related.
Okay, let's thank our speaker again. Next up, we have Jessica Zabrowski, who's going to be talking about probing the Middle Ages of cosmic history with line intensity mapping.
Hi, so I'm Jessica Zabrowski. Oh, how do I it backwards? And the talk title that I submitted was Probing the Middle Ages of Cosmic History with Line Intensity Mapping, but I changed it to a more appropriate title, the Terahertz Intensity Mapper Test Flight, the Hopes and Heartbreak of Scientific Ballooning. So let's start with the line intensity mapping. So here we have a sort of familiar picture of our universe many cosmologists love and have on their, wall in their office. Starting on the left with the Big Bang, this hot, dense point of our universe's beginning. And as you move to the right on this diagram, this signifies the progression of time. You see the cone expanding, signifying the expansion of the universe. And so at the far right side, we have the familiar structures, galaxies, stars that all of you study and love today. So despite having this rough idea of the history of the universe, we still have very many unsolved mysteries that I'm personally extremely interested in. For example, what is dark energy, what mechanism drove inflation, and how did the first stars and galaxies form? And to answer these questions, many people are studying different points of cosmic history. At the beginning, you have people making measurements of the CMB. At the end, you have people working with data, as many of you in this room do, studying our galaxies and our local universe. But honestly, most of the measurements that have been made are the two endpoints, the beginning of time and the end of time. And what I'm personally really interested in is using this new technique called line intensity mapping, using emission from atomic and molecular spectral lines from galaxies, such as carbon monoxide, ionized carbon, hydrogen, etc., to map the 3D galaxy distribution and fill in the gap from early time to late time measurements to get this complete picture of the universe's history and hopefully answer some of these big cosmological questions. And for me, it's this cosmology that really drives me to do these line intensity mapping measurements. So line intensity mapping can potentially constrain cosmological parameters beyond the current CMB limits and galaxy survey constraints. So this plot on the right shows improvement over plot that you could get from line intensity mapping in terms of parameter constraints, which are plotted in rainbow up at the top. So you can get inflation in the history of the early universe, neutrino masses, new light-rally particles, dark energy. And so the name of the game is going from the left of this plot. We're about here right now in current instrumental sensitivity, and my research centers on how we can get farther to the right and get these orders of magnitude improvement over current cosmological constraints by building better instruments to do line intensity mapping. So now that you've decided that you're on board with line intensity mapping, you have to pick which line you want to intensity map. And in this picture, or this plot, you have some of the familiar lines that people sort of bump around about line intensity mapping. How you read this is the y-axis is the line brightness of the signal, the strength of the signal, and on the x-axis is frequency, so where it shows up in frequency, like what kind of detector you would fill. You see the familiar peaks of carbon monoxide, you see ionized carbon, and then the rainbow color scale refers to at what redshift you're measuring it at. And in my opinion, there are only two places that really make sense to measure on this plot. And you either need to go, oh, you can't really see this highlighted boxes. You either need to go to CO, which is right here in gigahertz, and that's the maximum signal bet. You're saying, okay, that is just literally the brightest point on the plot. And that's going to be easier because it's the brightest signal. You can build, a less sensitive detector and still measure it. And then the other gamut I think you can take is C2, which is the maximum signal to noise. So with CO, you have a bunch of different CO lines. It combines to add to the highest signal, but it's a little bit confusing. With C2, if you make a map at 800 gigahertz, you're pretty much only getting C2 at one redshift. So these are the two places I think that make sense to do line intensity mapping. Now, most of the time that I've been an Einstein Fellow, I've talked about this experiment, STScI, which does CO carbon monoxide line intensity mapping. That's going great. We have a bunch of experiments, we have a bunch of equipment up at the lab. We have price that works, you have detectors, you have beautiful spectrometer data this year. And that is deploying to the South Pole this winter, so stay tuned for more exciting results from STScI experiments. But today I'm actually going to talk to you about a project that I've been working on this week, which is the terahertz intensity mapper, which is a balloon-based experiment that's going to do terahertz line intensity mapping, so mapping the C2, and since it's balloon-based, you're doing it from space. And you may ask why you need to do it from space, and this blue line in this figure really shows why. So it is the atmospheric absorption. So if it's low, you can see through the atmosphere, and if it's high, you can't. So if you want to go up to the C2 peak, you see that this light blue line is really high up. You can really only do this with a balloon-based or satellite mission, so you need to go into space. So terahertz intensity mapper, TIM is a collaboration with many institutions, Illinois here at Caltech, JPL, ASU, Arizona, and Penn. Our PI is Joaquin Vieira at Illinois. I'm the co-I in charge of the analysis for TIM, so I am putting together the forecast, teaching the grad students and getting them up and running on the analysis pipeline and thinking about how, when we get this data, we'll be able to use it to start doing some really cool line intensity mapping of C2. So the TIM survey is going to do a deep 0.1 degrees squared field. It'll have this shape, and that's because we have a diffraction gradient spectrometer, so all detectors are aligned in a slit. So we just take our slit detectors and go back and forth, and get this really deep squared 0.1 degrees squared patch that'll be centered at the good staff field. And what this measurement actually is that you measure these low resolution intensity maps of C2 as a function of frequency, it's a spectrometer, and this traces the large scale structure in the underlying galaxy population and dark matter distribution as it evolves over time as the spectral line redshifts. So what you get out is this stack of maps. And a lot of people find this more easily to visualize with a cube. So you have this 0.1 square degree by 0.1 square degree square, that is your sort of observing spot in the sky. And then as you observe it at many frequencies, it turns into a cube that evolves with redshift. from redshift of 0.36 to 1.7. But again, remember, you're actually getting mass. So you'll have like 1.65 redshift map. You'll have your 1.1 redshift map. You'll have your 1.34 redshift map. And what really makes these data unique and different than other experiments observed in the terahertz is that this tiny cutout of our 0.1 degree by 0.1 degree box, this is the ALMA full width half max. So if ALMA wanted to survey this cube, it would take like 12,000 years. And we've only had like 30 hours of bandfold data ever. So we can hit this in 200 hours of one antarctic spaceflight and get this data, which is basically impossible to get from the ground. And even with this a simple cube, you can do just really simple data analysis things and start learning interesting things about the universe. So the first thing is a direct detection. You can take these different line of sight to the cube, which are in rainbow here, and you plot their intensity as a function of redshift. You see when things pop out. You see how many emitters of C2 you can detect. And just saying how many, the number density that we see in the TIM field, starts to train different C2 luminosity models. So you're just taking the most basic analysis you can imagine. How many blobs do we detect? You're already constraining the C2 luminosity function. And of course, you can do fancier things. Because we have many of you who work on galaxy catalogs, we know where galaxies are. So if we stack on the location of known C2 emitters as a function of redshift, we can see how this evolves. We can see changes in star formation modes, metallicity, and specific star formation rate. And of course, because we know where the galaxies are, instead of just stacking on them, we can start getting into the real bread and butter of line intensity mapping, these power structure measurements. So you can do a C2 galaxy cross power structure measurements. So here in blue and green are all the different models of C2 intensity. And you can see that with TIM, like a 200-hour flight, you're really sensitive to all the proposed models that are sort of reasonable in model space. And this constraint on the C2 luminosity function really can be directly translated into a measurement of the cosmic star formation history. We can also obviously do the auto structure just using TIM data. And what I think is really interesting here is, again, just the C2 luminosity function and a function of K. And you can see that, like, for 200 hours, which is what people get our flight, we're really rolling out all of parameter space. So we're really being able to detect all of parameter space. But even if we only get 15 hours on the sky and we cut down a really short truncated flight, we're still making really interesting constraints on different models. So this is the TIM science that I'm really interested in, this direct detection, the stacking, and of course the power spectra that are going to be turning into this and paving the way for these cosmological constraints. But even if this first Pathfinder sort of 200-hour flight, we're already saying really interesting things about the star formation, right? So the actual instrument in itself is an Antarctic stratospheric balloon. We have a big 2-meter primary mirror with a capsularine design. We're going to have a liquid helium cryostat with a sorption cooler to get us down to 250 millikelvin. 2 grading spectrometers that'll splay our frequency out amongst 2 kit arrays with about 3,600 detectors each. And scientific ballooning, if you're not familiar, the thing that's cool is it isn't, a party balloon. This balloon is literally going into space. So you can see here, you're getting above the Earth's atmosphere, you're dangling a telescope from a balloon. And this is a really big balloon. As you're put for scale, like this is the Washington Monument, and this is the balloon. So this isn't, Party City. This is huge, huge. And trying to get these telescopes up and launched is a big, big logistical lift. And to do this, you have to pass 3 major checks. And this is what I've been working on this summer. So the first one is a test flight. We've been doing it this summer at Fort Sumner, New Mexico. So your payload will fly. You don't have any detectors on it. You test your communication functions. And of course, you don't take science data because there's no detectors. The next thing we'll do is next summer, we'll do a hang test in Palestine. So there'll be no flight, but we'll take and hang our payload on a crane with the cryostat fold, prove that our receiver and detectors work. We'll test it into communications and scan it and stuff like that. But you get no science data. And then science flight will happen about winter after that. So 26, 27, about, somewhere in January 2027. The payload will fly, the cryostat will fold, we'll have communication functions. This is when we'll get our science data with a flight from McMurdo, Antarctica. But this summer, we've been out in Fort Sumner, New Mexico. We arrived in early August, built things up, and right now we're in our flight window. You might ask, where is Fort Sumner, New Mexico? It's really in the middle of nowhere. The nice and Peloton is a Super 8, and the only place that we've been around is $190 now. So we've been spending all of our time in the NASA hangar out in Fort Sumner. They have a really big high bay where you can go out and build your scientific balloons. We've built up the sun shield and the solar shades. So basically, this is the instrument that you'll see. It's very similar to the BLAST TNG design, but instead of a receiver, we have a block of concrete with the same mass as our receiver for test flight purposes. So we went out there, we built up the solar shield, so you can see all the aluminized mylar and construction happening together. Rigging up the gondola, you can see me in the center there in my cargo pants turning screws. Leveling it because you need the pivot to work perfectly and be perfectly balanced so that you can point where you think you are. This is the whole team, and it's actually a pretty big experiment. I'm gonna skip through some of this because I'm running out of time. This is a picture I took 3 days ago with the whole TIM gondola built up and ready for launch. So a typical launch night goes something like this. You show up at 11 p.m., you show up and prep your payload. At 1 a.m., the science team, which is us, says we're ready to go. And the safety comes out and says, it checks the weather, checks the flight path, make sure we won't fly over any major towns because you don't want this thing coming crashing down in a major town. At 2 a.m., they integrate the electronics that the NASA people have. 3 a.m., you hang on the launch vehicle with the weather all clear. At 4 a.m., you inflate the balloon. You can see this is a picture of a real launch in McMurdo, the payload hanging on the launch vehicle, and the balloon up to the left. Over to the right is us hanging on the launch vehicle. Then 7 a.m. you launch. Now, so far what we've had is a typical launch attempt nights, where instead of inflating the balloon, we'll be sitting there hanging on the tarmac waiting for the weather to change, which it hasn't. And at 7 a.m. instead, we'll pack the payload, get a sad breakfast that'll only dine on the town, sleep until 3 p.m., and then at 11 p.m. that night is repeat. So I've been doing this for the last 5 days out in Fort Sumner, New Mexico. On Sunday, at 7 a.m., I packed the payload and I booked a flight to the NASA Hubble Fellowship Symposium because I knew that the weather is going to be bad for the next 2 days. And I will be here until they tell me the weather is good again, and then I'm going to book a flight back to Fort Sumner and continue to try to get this thing off the ground this summer. So that's where we are. Tim's waiting in the hangar in our flight window, waiting for good weather to break from Fort Sumner. But to really put this into context, although it's been a lot of hurry up and wait, and I'm definitely still slightly nocturnal and did oversleep by an hour this morning because I'm used to that being my daytime. Things are happening flying since the we're building things like STScI swims going to the South Pole and taking data this winter. Tim is doing our test flight. This is not, just it's off the page of the proposal and into reality with real hardware. And this should fly to be able to do some amazing cross correlation science between the two experiments soon. So yeah, that's all I have to share with you today. And just stay tuned for some real data in the future. Thank you.
Hey, thank you. One quick question while our next speaker comes up. Yeah, over here.
So this is really cool. I'm just curious, in Antarctica in a few years, like, what are the weather requirements like?
So this has been why it is so difficult to get this launch off the ground. You need to have winds below 10 knots, and you can't have any shear for 1,400 meters going up. Because if you have this football field sized balloon going one way or payload going the other, number one, that's really dangerous and it's bad for your science payload. So as we're waiting for the launch conditions to happen, what we're doing is every half hour, we're sending up a test balloon with a blinky light and seeing if it goes straight up. And they have really complicated meteorology data to be able to do upper atmosphere models. So you basically need a completely still day to be able to launch. So this season from Fort Sumner, they've launched 2 balloons so far. We're the next on deck, and there's about 10 days of the season left for us to get a launch window before the winds change until next summer, and it's completely impossible to launch. So everyone send really calm wind vibes towards the New Mexico desert for me. Thank you. Yeah.
All right, let's thank Jessica again. And next up, we have Justin Perrell, who will be telling us about Type 1A supernovae and JWC.
Great, thanks. Yeah, I'm Justin Perrell. I'm an Einstein Fellow at Space Telescope, and you can see I changed the title from the one on the program. This is actually the title of the JWC program that is going to get data relevant to the talk. We tried something similar to the title that's on the program 2 cycles ago, didn't go through. Fun title went through, so that's your lesson from the talk. Make fun titles for your proposals. So, okay, which one needs to switch? Yeah, okay. So obviously a broad science range here. Not everyone cares about Type 1A supernovae or cosmology. So I start with a little why should you care slide. So the primary purpose, of course, is cosmology. It's why it's the cosmology section. So things related to the Hubble constant, evolving dark energy, got a very nice intro in the first few slides from that. So I'm excited about not needing to go into too many background details. And then There's also a significant overlap with people who care about galaxies, in particular high redshift galaxies. We have been collaborating a lot with people interested in high-Z galaxies observed with JWST because we get a lot of spectroscopy, in particular multi-object spectroscopy, where to us we need filler objects, to you need primary targets. And we also get a lot of repeated imaging of fields, which of course stacked up get some of the deepest imaging that exists with JWST so far. Then, of course, you might just not care. That's okay. Lots of talks. You can let your eyes glaze over for a few minutes, and we'll be back after the break. Okay, so you saw some version of this already, which is great. It's basically distance on the y-axis and redshift on the x-axis for our sample of spectroscopically confirmed in black type 1a supernovae before the launch of JWST. And then at the edge, all found with Hubble, we have the photometric sample. Photo-Zs and or photometrically classified as type 1as. There's no spectrum showing that this is actually a type 1a supernova. And then a couple of gravitationally lensed, not multiply imaged, but just gravitationally lensed type 1a supernovae that are our most distant discovered with Hubble so far. And I'm going to put a line here at redshift 1.5, which turns out to be an important redshift. I'll say why. I forget the red line is lambda CDM, as we just talked about multiple times. So now these lines, you can ignore the W numbers, but basically these are relative to lambda CDM, a few ways that dark energy could plausibly be varying as a function of redshift out to Z of 1.5. And you can see a reasonably large change of about 10% over this redshift range. What I want to just kind of bring into your mind is the possibility that if you're trying to measure this change with redshift, does this actually? Yes, just change with redshift. So imagine type 1a supernovae that suddenly diverge from lambda CDM, and we see this, okay, yes, there's evolving dark energy, but what if 1as themselves are changing with redshift? So this is a simulation showing two plausible scenarios. Blue is our dream. No evolution with redshift. So we're measuring our 1as, we're out at redshift 3. They look just like they did at low redshift, and we can confirm, whatever measurement we make. There's evolving dark energy, there isn't, no problem. But you can imagine a lot of things that could impact type 1a brightnesses with redshift. For example, this is a simulation with metallicity, which could plausibly change the brightness of a 1a with redshift. So you can see maybe with metallicity changing with redshift, our 1as are just systematically brighter at high redshift. They're no longer standard in the same way that we see them at low redshift. And that would bias your measurement. You would see these evolving distances. You would say that's evolving dark energy, but in reality, it's just evolving type 1a supernova. Well, the nice thing about this redshift 1.5 is if you continue this out beyond redshift 1.5, the difference of evolving dark energy beyond 1.5 is quite small. You're in the dark matter dominated universe, and therefore, if you were to measure type 1a distances in this redshift range and see that they were changing up into this range, you could be fairly confident that it's not from evolving dark energy. It's probably due to that evolving type 1a supernova brightness. And so we'd like to find them in this range. We're going back to this plot and zooming in, you can see this is where we're at. We have one, that's this black here, that is spectroscopically confirmed at redshift 1.6. And then the rest of the sample is either photometrically classified, which is just not really our pristine cosmology sample, or gravitationally lensed, which brings in lots of systematics. So we want more in this range. And that one that's at 1.6 is the one on the right here, spectroscopically classified with HST. It's not great. This is a borderline classification, I would say. And then the next highest at 1.3 is definitely better. So this is sort of the state of the art leading into JWST. Okay, so where did we get to now? So the talk title, that's an ongoing JWST program. It just started. We have triggered once and we're in the midst of getting our data, but we are expecting to get 10 points on that plot the next 2 cycles. So hopefully next year, I'll have a whole bunch more. But what we've done so far is in serendipitous discovery. So in deep galaxy surveys that just happen to overlap with other JWST observations that we were then able to get subsequent director's discretionary follow-up to learn more about the transients that we found in the field. And with that, we found 2 type 1a supernovae. So the first, this was in the JADES Galaxy Survey, which is some of the deepest JWST imaging that exists, down to about 31st magnitude, which is absurd. And the supernova here, this is the difference between imaging taken in 2023 and 2022. And you can see these are difference images that the supernova really pops out, especially in these red filters. So as you go from left to right, top to bottom, you're going to redder and redder wavelengths. This is a little bit strange. We expect type 1a supernovae to be on the bluer side. So this was already a little bit weird. We looked at the spectrum. This is the spectrum observed in black, just shown 5 times. And it's being compared to the top 3 are kind of common core collapse, non-type 1a subtypes. And then the bottom 2 are type 1a spectra of slightly different types. And the idea of spectroscopic classification is which one matches best. That's basically all we do. We look at low redshift spectra that are well observed, we compare them to our new spectrum, and we say, okay, this looks like that. Okay, it's probably a type 1a supernova. Just for reference, this is what we called type 1a supernovae before on the right. So basically, I'm telling you that statistically, this is the best fit. And it's not maybe any worse than these, but if you have a trained eye, you might see some missing features. And basically, we were unable to say, just from the spectrum alone, that this wasn't 3 core collapse supernovae masquerading in a trench coat, and say for sure that this was a type 1a supernova. So we went to the photometry. This is a normal type 1a model in blue, fitting the photometry in 6 filters at redshift 2.9. And you can see, I think it's a very good fit. And basically, we did the same thing with a bunch of core collapse models. The end result is between the combined information of the spectrum and the photometry, we do think this is a type 1a supernova. But it is weird. It is very red. It's blue minus, so it's B minus V. Color is about 0.9 and magnitudes, and normal is more like between minus 0.4 and 0.4. It's not unheard of, but it's definitely strange. This is the first type 1a supernova in this redshift range, so we don't know whether that's just normal at this redshift range or we found a weird one. I would say, like I said, the combined information is that this is type 1a, but still plausibly 3 core collapse supernovae masquerading in a trench coat. So the only thing we can really do at this point is get more galaxy information, come back and get more spectroscopy of the galaxy. It could give us more information about the environment and a better subtraction for the supernova spectrum that could improve this classification. Okay, so the second one was in the Cosmos Web field. So that was observed back in December of last year. And for those of you who do lensing science, just for fun, this is actually a galaxy scale lens that we discovered in the field. So that's just a fun little thing. Anyways, this is the supernova here in blue, and much more blue and normal looking from just a generic type 1a supernova side of things. This one's at redshift 2.15. So lower than the other, but still within the new redshift range that we just haven't really looked at before. And the spectrum looks very normal. So compared to what you saw before and compared to HST, this one is a definite type 1a supernova. The red is just a classic normal 1a at low redshift. The black is our observed spectrum at 2.15. And this is just like a kind of a rock solid fit. This one, though, happens to also be slightly strange. It's actually very blue. So the other one, very red, this one quite blue, but within the normal cosmology cut range. So this is the first high redshift 1A that is within kind of normal low Z cosmology cuts, but it is at the blue end. So we have a very blue one and a very red one. And the main question is, where do they fall in the Hubble diagram? And the answer is basically on normal lambda CDM. So of course, 2 is not enough. That's why we have the new program to get 10. But for the first 2, no indication of significant evolution with redshift. But expect to see this filled in between redshifts 2 and 4 in the next year or 2. So we've been looking for, type 1a supernovae, but we've accidentally and on purpose found lots of other really cool stuff. So I'm just going to pop up some plots that then anyone can talk to me about in the breaks. So we found very bright, very blue core collapse supernova at redshift 3.5. That's the highest redshift supernova spectrum that exists. And we're in the midst of doing this. We have a whole light curve as well that goes with this. We have a type 1c broad line at redshift 2.8, easily the highest redshift version of this. So the first one of these I meant to mention is being led by David Coulter in our group, and the second by Matt Siebert. We found there have been two multiply imaged type 1a supernovae at redshift 1.8 and at redshift 2. The first on the right has already produced a measurement of the Hubble constant that agrees with, within a couple sigma technically with both, but it is on the high end. So in terms of the Hubble tension, it is in the mid 70s, so in agreement with Shoes in particular. And then on the left, this one is going to produce another measurement of the Hubble constant. So that will bring our total multiply imaged supernova H0 measurements to 3. And we actually just found potentially another one of these and triggered a program. So if anyone wants to talk about that, I'm happy to discuss that as well. And that is it, some highlights there. So you might still not care about type 1a supernovae at high redshift, that's fine, but we are doing lots of other stuff, finding lots of core collapse supernovae, looking for TDEs, finding AGN, and having lots of multi-object spectroscopy that covers other galaxies that you might be interested in. We have a sample of 2 right now, type 1a supernovae at redshift greater than 2, the first 2 spectroscopically confirmed non-lensed type 1a supernovae at redshift greater than 2. We're expecting 10 more in the next 2 cycles. And no initial evidence for luminosity evolution, but we will keep checking. And then lots of other cool stuff. Happy to chat about it in the breaks. Thanks.
Hey, question, yes. Repeat the question.
Do you have the live from the light curve at the most distant supernova spectra that you showed?
I actually don't, but I have it. I should have added the extra slides, but for some reason didn't for the first time ever. Just come find me, I have it. It's extremely blue and quite bright. Oh, sorry, the question was, do you have a slide showing the light curve of that high redshift 3.5 type 2?
So there's been analogies between gamma ray burst and of course high redshift and supernova we see broad line region. Any analogy that you can spot on between the one that you found redshift 2 plus 2.8 and any of the gamma ray bursts?
Yeah, so the question is whether we found gamma ray burst candidates or look for gamma ray burst candidates for the 1C broadline, because there's been a lot of discussion of the connection between those. So all I can say is that we looked and there was nothing that was obviously associated with it.
I meant on the spectra of the supernova and the supernova associated with the GRBs.
Oh, well, I just mean we looked for GRBs at the same time, but no.
No, I was looking about the supernova associated with GRBs.
Oh, yeah, I don't think so. You can look at the paper because Matt led it and he's the 1C broadline guy. But I think the answer to that is no. But the interesting thing that basically came out of that is like, it seems fairly normal for 1C broadline, but they're pretty rare. So it's weird that it was one of our first high redshift supernova discoveries. So that was kind of the interesting thing that came out of it. It was like one of the first 5 high redshift supernovae that we found. Yeah, they're bright, but this was a 31st magnitude survey. So we're sensitive to everything basically. And this was one of the first ones. So that was kind of weird.
Move our next speaker, come up, please.
2 non-type 1a questions about a type 1a talk. So that's it.
Any other questions?
Presumably, I don't know much about this, but presumably you need a luminosity distance, like from the light curve. Yeah, we didn't see any light curves. I'm wondering how many points you need or how you do that.
So the question is about measuring luminosity distances from the light curve. I did show one. I showed the fit to the one that had the 3 core collapse supernovae in the trench coat. So there's the light curve there. So basically, JWST not very efficient at getting light curves. That's the problem. It does have excellent SED sampling though. We've been getting 3 to 4 light curve epochs per supernova in 6 to 8 filters. Seems to be enough. The typical distance uncertainty has been about 15%, 15-20%, which is higher than we can do from the ground, but not terrible. Thanks.
Cool. Thank you so much. Let's thank Justin again. Okay, so next up, we have Christian Garcia Quintero. who will be telling us about constraining dark energies. Right ahead.
Thank you so much. You pronounce it very well, actually. Yeah, indeed. Yeah, well, hello, my name is Cristian Garcia Quintero, and I'm very happy to be here. It's my first time in the symposium. And I just started, in fact, my postdoc at Harvard a couple of weeks ago. So the title of my talk is very general, but basically I work in DESI with Andre, and the title is Constrained Dark Energy and Modify Gravity using Basic Galaxy Surveys. So Andre already did a very good job in describing what DESI is. So I'll just mention quickly that DESI is an instrument that basically tries to measure the galaxy redshifts by using spectroscopy. And the takeaway message is that over a period of 5 years, is going to approximately measure 40 million galaxy redshifts while covering 14,000 square degrees. And Andrea already told you about the different tracers that we are observing. Andre focuses a lot on Lyman alpha. However, in my case, I focus more on the galaxy clustering side of things. Because as you heard on the first talk, DESI can build a 3D map of the universe and why it is important. I will just reinforce on what Andre commented to you about BAO. So basically with DESI, with that 3D map, we can measure baryon acoustic oscillations. And if you want to understand what baryon acoustic oscillations are, you need to go back with me before recombination, where the universe was a plasma. And this plasma, you can think that was made of 3 main components. You have dark matter particles, they only interact gravitationally, and therefore they are going to form overdensities. And then we have the baryons that are going to try to go and cluster around these overdensities. However, in this plasma, we also have the photons, which by doing scattering, will exert an outward radiation pressure away from these overdensities into the baryons, and that will lead into an oscillation pattern in the baryons. Basically, this will translate to sound waves propagating the plasma, and as the universe cools down, basically you are going to start seeing that the protons combine with electrons to form neutral hydrogen, and as the number density of the electrons go down, then the scattering rate of the photons with the electrons is going to drop, and you are going to have decoupling. When this happens, basically you stop the oscillations. However, all these different oscillation modes, we care about one mode in particular, which is the longest oscillation that goes all the way from the Big Bang till the time of recombination. And that defines a sound horizon, which is going to happen at various parts of the universe, and it's going to define this standard ruler that Andre was talking to you about. Because it's a standard ruler, because when you project it through the redshift as the expansion of the universe happens, then in principle, you are going to find that this left an imprint in the galaxy clustering history of the universe. And how can we measure it? Very simple, conceptually. Basically, you start counting pairs of galaxies and measuring the probability of finding a pair of galaxies at different scales. That will build a two-point correlation function, and you're going to find some peaks. The first peak that happens at small separations is governed by the dark matter, because it was always there. But then this function is going to drop. And at a given scale, which is the scale of this ruler projected to the redshift, you are going to find a bump. That bump tells you that there is a scale in which you find excess of galaxies, and that's a view feature that we are trying to measure. That's just a cartoon, and basically here you can see the measurement of the view for one of the tracers that Andre was talking to you, which is the luminous res galaxy tracer. Effectively, how you measure these parameters, you have 2 parameters, alpha iso, which tells you the isotropic scale of these shells, and then you have another parameter, alpha IP, that tells you the isotropic warping into this scale, because then you're going to also have a nonlinear growth of a structure that is going to deform and not make this thing very isotropic. The important thing is that you can isolate the BAO into a template and get the information out of these 2 parameters, but these ones, at the same time, they translate to cosmological distances. And then with the likelihood analysis, you can basically get constraints on the cosmological parameters. That is what we ultimately care. Basically, my talk is divided into 2 parts, so I will just tell you that we got the measurements on the BAO and just few remarks there. Basically, DESI, just with year 1 of data, show a better aggregate precision compared to SDSS, around 20% better aggregate precision. This was the first time that we did a catalog blinded analysis of BAO, and the LG tracer actually has more protagonism in this analysis. Andrea will talk to you about the different degeneracy directions when you start combining these different probes. So that shows the complementarity of the probes given the degeneracy direction. And we find a small tension with SDSS that I can tell you more about in the questions if you want. And basically, one of the things I was leading in that analysis was basically working on biosystematics, because ultimately the statistical error that you report to the community needs to account for systematics, otherwise you won't believe it, right? But mainly among all the systematics that we took into account, there were three main systematics, which at the end, all of them turned out to be subdominant. So we have a theoretical systematic associated to the template approach in which how we isolate the BO feature. We also have systematics related to the HOD modeling that you were assuming when you were building the models. So here you can see basically measurements of the BO parameters when you start checking various HOD recipes. HOD is scale of patient distribution, but you see that any dispersion given the HOD model that you assume in the measurements, all this dispersion is actually way below the statistical error that you would obtain with DESI, and that's what you actually want. We also test things such as the impact of the fiducial cosmology you assume when, for example, you translate redshifts into distances. And we ultimately got results in cosmological parameters. In particular, one that was kind of a boom in the community was the results that Andre showed you on dark energy parameters, because for a long time, people is saying that basically the cosmical constant is the recipe for producing the cosmic acceleration. However, it's not only due to DESI, but the complementarity, I have to say, between DESI and supernova data, as well as CMB, that you start seeing some indications of a possible departure when you move to this stage 4 surveys, such as DESI. But this still will be on the eye of the people, but when you go to year 5, year 3, you are going to start seeing more closely what's going on. However, the second part of my talk, and what I wanted to tell you about is what other things we can do with DESI, because you have such a very nice survey, so ideally you want to exploit fully that information. And a way to do it is that you can notice that DESI, I told you that it covers 14,000 square degrees when it goes to 5 years of observation. However, there are other surveys that are not the spectroscopic surveys, but they are imaging surveys. They are not very good at localizing the galaxy, but they can also tell you information about the ellipticity of the galaxy that will overlap the DESI footprint. In particular, from this figure, you can see that DS03 has 900 square degrees of overlap with DESI. So conceptually, what you can do is that you can do galaxy cluster analysis with DESI. You can also use the correlations between the ellipticities of the galaxies and do what we call cosmic shear. But if there is an overlap in the footprint of the two surveys, you can do a cross correlation between the two, and that's what we call galaxy-galaxy lensing. This is already being tested on MOX, and probably you will hear more about it in October, hopefully. But basically, you can see that we are testing our analysis pipeline by using MOX that involve the DESI and these imaging surveys. And you can see that red plot is the confidence contours that you get when you use cosmic shear. The green contours is the galaxy cluster information from DESI, and the galaxy-galaxy lensing information when you cross-correlate. And then you can do the 3 times 2 point analysis, which is basically combining all of that and shrink a bit more the contours. And that's also shows you the complementarity of the different probes. 3 minutes, okay, perfect. So ultimately, what I would like to do is that all these plots that me and Andre showed you about dark energy is because you want to understand what is causing the cosmic acceleration in the universe. However, you cannot rule out, and you have a lot of data, and you should also look for modifications in the underlying theory of gravity when you go to very large scales. So there are 2 ways to test modified gravity. One is you have a particular model that you like, and you go and test and go under that model. The other way to do is that you can try for a more phenomenological approach in which you modify the linear perturbed Einstein equations and you introduce these arbitrary functions. Then, if you later on constrain these functions and their value is equal to 1, basically you are consistent with the error. However, if you find that any of these parameters of these functions have a different value, it might be that either there is some systematics on your analysis going on, or if you remove everything, is that it might be a different theory of gravity telling you how the things are behaving. Just very simple, we have a parameter mu of A that it's basically acts as an effective gravitational constant, so it affects the strength of the gravitational interaction. You have another function called sigma, which affects the biopotential. This biopotential, it actually affects the deflection angle in weak lensing. And when you propagate this definition, this red box and this blue box into cosmological observables, you will end up finding that this mu affects the growth of the density perturbations, and this sigma affects what we call cosmic shear and these galaxy-galaxy lensing signals. What you want to do is the same that we did with dark energy, which is basically using the multi-probe analysis. Because one probe is not enough, you need to use as many as you can. So basically, this gray plot here tells you the constraint on the modified gravity parameters when you use CME data, and also growth rate of structure data from redshift space distortion. And then when you include the weak lensing information from CMB or this imaging service, then you shrink the contours, and then you get the green contour, which is basically constraining the full modified gravity parameter space. And in this paper, we found that everything was consistent with GR, which is what you usually find. But we are planning to repeat this analysis now with DESI. Just to finish, I will say that we have a software called Integrated Software in Testing General Relativity. The acronym is ECGR. I don't know if you get it. I think it's a very nice name. But basically, this software is integrating into the cosmological analysis pipeline of current stage 4 surveys, such as DESI and LSST. So basically, in the same time, we are using the DESI data to look for a different model of dark energy. If you complement this with this imaging service, you can also constrain modified gravity parameters. And that's all. Thank you so much. I think I got in 15, right, Maurice?
Yeah, very good. Questions?
Otherwise, in the launch as well. So.
You explained it so well. Anybody
No,
have any questions? Well, we are running a little bit behind time, so maybe we should move to, I think Jen is online, maybe.
Hi there, I'm online.
So I'm just going to.
Yeah, I think I'm questions, but I'll get them to you later.
Yeah, it's good talk. Cut the share to go.
Hi, Jen. We can see you, but I think, can you see us over there?
I see you, Andy. I don't see all the audience,
Okay, well.
but that's okay.
So what you do is rotate that stand, right? So, okay, I'll do that in a minute. So first, we have with us Jen Lofts, who is the new director at STScI. She joined earlier this year. She was previously the director at Gemini, and before that, she was at Space Telescope as a staff member. And so she knows the Institute very well, and she's a really fun person. So you'll enjoy meeting her next year when the symposium is back at Space Telescope, hopefully. But this year, Jen has agreed to join us remotely and give us a little welcome. And then if have some questions for her, I think we'll have a little time for that too. So, okay, Jen, go ahead.
Okay, great. I do have a few slides. Is it possible to share my screen?
Yes. You should have a button to do that up at the top or something.
Okay. Now I think I can do that.
Go get it. I'm sorry, we're rotating this. If it falls over, well, I don't know. I'm going to do that before with this. All right.
Okay. Now. Okay. So I'm sorry I can't be there in person, but I look very much forward to seeing everyone next year. I'll say I did my graduate work at Johns Hopkins, and I would always walk across the street for the Hubble Fellows Symposium when I was a student. I learned a tremendous amount. And so, and I see you have a really excellent set of talks this week. I hope that you're enjoying this week and that you get out as much as I did out of the symposium every year. I just wanted to share with you a few things that I thought you might want to know as Hubble, Sagan, Einstein Fellows, if I were sitting in your role. You know, we're in a really exciting time for astronomy when a lot of really fundamental, amazing questions are being asked, and we actually have a hope of answering them. You know, when did the first stars and galaxies form? What is the nature of our universe? What are our cosmic origins? And even starting to get at the question, is there life on other planets? So at the Institute, we are the Science Operations Center for the Hubble Space Telescope, the Science and Mission Operations Center for the James Webb Space Telescope, and we'll be the Science Operations Center for part of Roman, leading the Wide Field Infrared, the Wide Field instrument. So Hubble, you know, continues to be an amazing powerhouse for a broad range of science. It has unique ultraviolet and optical capabilities that will be unsurpassed until the Habitable Worlds Observatory comes into being. Last year was really a record year for Hubble publications. We had a really strong oversubscription rate, and thanks to Dual Anonymous, a third of those PIs are new PIs. In June, you may have heard that Hubble transitioned to reduced gyro mode. This will have no impact to the quality of the data that's being taken. Actually, Hubble was already taking data in reduced gyro mode, and it was using its 3 gyros just for slewing. There will be an impact to efficiency, but we expect Hubble to perform well into the 2030s. You're probably aware that we're facing potential budget cuts. Those budget cuts are likely to impact what instrument modes will be available in cycle 33. And so I would just stay tuned. We'll be having more community engagement soon on this, letting people know what our immediate plans are. It does look like we are going to be able to fully execute what cycle 32 programs look like. But this amazing long legacy with Hubble really allows us to now start doing really interesting kinds of science that you couldn't do without, you know, decades worth of observations. Most recently, this observation paper looked at 20 years of observations of the Omega Cent globular cluster, was able to detect 7 fast-moving stars within the center of that globular cluster, which is evidence for a central black hole that has a mass that's 8,000 times the mass of our sun, one of these intermediate massive black holes, which is a pretty interesting kind of black hole. And that's really only possible with a facility that has such a long baseline of very high quality public data. As many of you, I hope, are preparing for the cycle 4 proposal deadline for JWST. This is due in about a month's time. It seems to be delivering amazing scientific breakthroughs almost every week on a very broad range of science areas with over 900 papers published. The last cycle, cycle 3, broke records. We got over 1,900 proposals. There was a 9-to-1 oversubscription rate. Looking ahead to cycle 4, though, there's some good news. The number of hours that will be available to the community is going to be significantly larger. That's going to be increased to over 8,000 hours, 8,500 roughly. And that's because a lot of the big early programs from guaranteed time programs are complete now. One of the things that we will also be starting likely in cycle 4 is a new director's discretionary program focused on rocky worlds, and I'll say a little bit more about that in a moment. I'll just say that the observatory is performing very well. We're continuing to improve our data reduction pipeline. And if you're still having trouble with our pipeline, please reach out to us. But we're looking forward to a very long and successful future for James Webb. With Hubble and Webb operating really at their peak, I have this amazing opportunity to do some big programs with both Hubble and Webb working together. My predecessor convened a strategic initiatives working group on exoplanets, and their key recommendation was to do a survey of 15 to 20 rocky M-dwarf planets to try to detect atmospheres down to the habitable zone. So the idea here is to use both Webb and Hubble together. We'll be doing 500 hours of MIRI observations on Webb to probe the existence of atmospheres using secondary eclipse detections. We'll also be using about 250 orbits of HST cos-STS UV observations to characterize the activity of their host stars, to figure out how much radiation is coming from those host stars. And those things together will help us understand the cosmic shoreline for M-dwarf exoplanets. All of this data will be public. We have a science advisory group that's going to be helping us roll out how the community can get involved in analyzing this data. And we'll also be aiming to release the targets for this program well before the Cycle 4 proposal deadline, so that people know that as they're planning their Cycle 4 proposals. Coming up very soon is the Roman Space Telescope. So Roman is being built as a collaboration between NASA, particularly the Goddard Space Flight Center, JPL, who's leading the coronagraph development, IPAC, and Space Telescope Science Institute. So launch will happen no later than May 2027, and we're just about a year out from the first call for proposals. This is a different beast. Most of the time, 2/3, or I think about 3/4 of the time, is going to go towards large community surveys, with about 25% for general astrophysics observations. So the proposals will be largely for archival work, but you'll also have the opportunity to propose your own observations. And here you can see the comparison of the field of view for the WFI versus Webb and Hubble, as well as the difference in the overlap in the wavelengths. So Roman sits right between Webb and Hubble in terms of its wavelength coverage. What it will do is survey the sky extremely rapidly. So it's not just the larger field of view, but it's the fact that it can move across the sky very quickly, means that it will be able to survey nearby galaxies about 1,500 times faster than Hubble, image galaxy fields 1,000 times faster, and perform slitless spectroscopy galaxy surveys 700 times faster. All of that together makes for a very powerful survey telescope. So right now, the community surveys are being defined. There are 4 of them. There's a galactic bulge time domain survey. There's a high latitude wide area survey. There's a high latitude time domain survey, and there's an additional survey of the galactic plane being planned. So, it's not too soon to be thinking about what you might do with Roman, or how you might use Roman together with other telescopes. One of the ways you can find out more is to go look at the Roman Science Forum. You can hear about what's happening with the mission, as well as joining science working groups and getting additional information. One of the things we're planning to roll out soon is a prototype for the Roman Science Platform, and it would be great to get your feedback. The next thing on the horizon is the Habitable Worlds Observatory. And so if you were paying attention to the Astro 2020 decadal survey, you know that this was one of the key recommendations coming out of that National Academy's report, to have a large 8 meters or larger infrared optical ultraviolet telescope, which would provide both high contrast imaging for exoplanet studies and spectroscopy, as well as a broad range of capabilities for more general astrophysics. A lot of these capabilities are very much like Hubble. We're considering this a Hubble, super Hubble, that would be able to search for life in the universe, as well as perform transformative astrophysics. So I've got the website there if you want to see a little bit more. And my last real slide is just to get you thinking about what kinds of science you might be able to do with this. The science working groups are underway right now. They're putting together the initial science cases. Now that the Habitable Worlds Project Office has been stood up, this is becoming a real project. So it's certainly worth your time thinking about what would you do in the 2030s or early 2040s with this new kinds of facility. So it's not just for exoplanets. It's going to have an amazing set of capabilities. So with that, I will stop and see if there's questions on anything I just asked, and really encourage you to be thinking big and thinking about the long term in terms of how you can make the most of these new telescopes that will be coming online and the telescopes that we have now.
Okay, so Jen, so we have a microphone that we can pass around. Any questions for Jen? Yeah, that's wrong. But please introduce yourselves to Jen. It's Rohan Naidu, who are doing this time.
Hi, thank you so much. That is a wonderful overview. My name is Rohan Naidu. I'm an astronomy fellow. My question for you is about the DD, the really ambitious DD program that you described during the finals. I was curious, like, what plans you have to do similar programs in other communities, maybe like in following the great footsteps of extragalactic surveys like the ones that you led, like the Alpha Frontier fields. So just curious if, like, is there going to be a process for some communities to come together and like write like white papers, or is it going to be like something that you have to solicit, or like is there a constructive for it? Just curious what the plan is.
So I'm afraid I didn't get most of that. Maybe Andy, if you could repeat.
No, I didn't. I don't think I missed. Did you get you? What? Or maybe.
I believe it, since, well, you want to try one more time, or, okay. This
Well,
one is, I think Rohan was asking, if there were plans to kind of involve more communities in things like the Roman community that you're running together, right?
Right, my question, is this possible?
I think the mic is cutting out a little bit.
Maybe it's a position. We want to come down here. Run, Hilly, run down quickly. Yeah, it's okay.
Sorry.
You're coming through okay. But Rohan's not. Maybe it's the mask. The mask man.
Hello, Jen. Can you hear me now?
Yes, that's much better. Go ahead.
Okay, great. So it really is Mike. Yeah, so my question really was, like, you've put together this really impressive DDD program, the 500-hour program to do like these rocky worlds, right? So I was curious if you had plans to do similar such surveys in other communities, right? Like, for example, in the extragalactic community, you of course pioneered the frontier fields and so on. So I was curious if there's going to be some kind of like call for proposals, or is it like, do we like write like white papers? Like, how do we make this happen in other subfields that could benefit from similarly ambitious investments?
That's a great question. I'll say I'm also sitting on a report from another community, which is the long-term monitoring, which is thinking about how you might do long baseline observations, particularly with Webb. I mean, I showed you that result from Hubble, which is really only possible because we went back and looked at that globular cluster time and time again. And so if you imagine 20 years in the future, what observations do you wish you had taken with Webb such that you would have that 20-year baseline? So I'm sitting on that, and we'll likely move forward with some of that committee's recommendations. But certainly, DD time is both precious and exciting, and I'm looking forward to seeing how those two programs play out. But in a few years' time, I think, especially as we kind of get out of the first few years of Webb and start those really getting out of the, oh, wow, I can't believe it does this, to like figuring out what those really fundamental things that we understand about astronomy, where that's breaking, and how pushing Webb to its limits might help us make really tremendous advances that would require the investment of the scale of a DD program. So I'm not saying no, but I'm saying we've got a couple things we've got to do first.
Got it. Thank you so much. That was very helpful.
Yep.
Any other questions? If you have a question, you can come down and ask here.
Okay. Yeah, well, it's great. It's perfect timing though, because we're ready for a break. So thank you very much, Jen. We appreciate you joining us.
Okay, thank you.
Now we have a break until
12:20.
12:20. So right till 12:20, I believe there's copy and stuff out here. And you can join that or go back on the back.
It's great.
You can do like side by side, which allows you to see like the city I think that might be able to do live stream. But someone will find that you can't see it. I'm not sure. So I'm going to so the view. It's just like a spider. It's fun.
If we're on speaker, do instead of that, and someone shares. Yeah.
So
Probably get them these two people too. So please don't make that choice because the one that's picking itself. There are, yeah, I think there are 4 or 6 people. I've been on the so those gentlemen, so we have the next 3 until
Okay, everything going okay?
Yeah, great. Some of the remote presenters asked if they should just be sharing their screens.
That's the way we just
default,
that's the
right?
way we just did it. I did, yeah.
You did, okay, and then when happened. Okay.
Yeah.
As long as you-
And plugged it just so I could get
And
rid of
the
it.
laser pointer that you plugged in, because if memory serves, that laser pointer does not.
It doesn't
hold
survive
for
very long.
very
Okay, that's okay. I've got the charger ready for breaks and lunches.
Thank you.
Okay.
Okay. And we used to have, so we had 2, we had. Yes. Last week they had 2 handheld mics.
We have
There's another. Okay. Okay. And
I mean, we can. They yeah.
I wonder if one is louder
We tested
because
both of them, so. I mean, again, so
So that's for the
this,
speaker
yeah, those are our
putting in.
speakers.
Right, but these are for the handheld mics, or I don't know, when Pete came in, or this morning, when Chaz was talking, he was trying to think that.
it's pretty faint, those.
Yeah, so I don't know.
They're the same volume.
It says it's 2B, I mean,
Yeah.
there's WL1, WL2, WL3, podium, just to be at this one. M29 and M30.
Oh, those are muted.
Oh, those are muted, okay.
So those are not, because
Yeah.
these are working.
Yeah.
So, I mean, whatever these are, we could turn them up.
Yeah, Chaz was super quiet.
Yeah.
And then Rohan was super quiet.
Yeah. So
I don't know if
yeah,
these
sorry,
are
I know.
louder.
I got the other side, but I get the next question.
Well, we had a pretty simple question. It's pretty long-ended.
Okay.
Previous of our slides to make sure
Yes.
they're working.
Yeah.
Yes, please.
There's quite a few times I've seen PowerPoint to Mac conversions, horribly break all my fonts.
Yeah.
Yeah, so I am MacDonald later in the afternoon.
Okay, so this one you turned up.
See if this
and this one,
works.
because if there are two.
Okay.
So this is
Type slides. Looks good.
Seems correct.
Yeah.
Have
just
this
wanna
on. Yeah.
quickly jump through just to check that everything works.
It's not on the.
Yeah. Yeah, you see what I mean? That some of the fonts have resized in an interesting way. Yeah. Okay.
So if you talk, and then we're doing the photo.
Where?
We're gonna go.
I might do this. Can I just edit a few slides quickly? Like, is that possible? Or
If you do that, then please re-upload to the.
oh, but
to
the
the website.
problem is I can't do it on my end because everything looks fine on my end. That's the problem.
Right. I mean, yeah, you
Yeah,
be
because
able
all I
to.
have to do is just quickly drag the
Yeah, no,
box.
you
It'll
should
take me
be
like
able to.
2 minutes
Yeah.
to do.
Go ahead and try. Yeah, it's already downloaded here.
Yeah, you see that otherwise.
Right.
Yeah.
Yeah, I did that.
Okay,
Yeah. it's headphones.
Yeah, yeah. Okay.
okay.
Look,
We got a few minutes. Yeah, it did the problem that I thought it would do because Mac did terrible things. Yeah, you see some of the. So I just need to quickly shrink some font size, which I'm just going to do now to fix a few things. Yeah, otherwise my only other option is then to send a PDF, but that ruins all my beautiful animations.
No, if you have animations, we want to see them.
Worth worth trying to on the fly.
Yeah.
It's some quick adjustment.
Whoa, what just happened there?
Oh, sorry. I think Command S is slideshow on the Mac, which brutalizes me every single time too.
Fortunately for a 12-minute talk, there aren't that many slides. Okay. That's fine. Oh.
That was not a good thing.
Yeah, yeah. I had this at a conference. So whenever I hear you can't use your laptop, we're going to use a Mac, I go. Well, it's all right. These are easy fixes now that I. No, it's problem. You spend so long making polished slides and then conversions. Okay. Almost there now.
Yeah, so signal again in the city. And so they have to flag this.
It's just terrible.
Oh, powerful.
Yeah, I'm not sure why it is. It must just be that maybe the definition of size. It looks like all the font sizes are just like slightly off.
Always been like this. Like it's been doing this for 20 years. I mean,
I feel like I was slow.
Yeah.
I've heard that. I'm going to get all the speeches.
Almost there now.
Thank
you very much for letting me just do this. Yeah, because otherwise, this bit or something. Okay.
Yes. It's all different phenomenon.
Oh,
Yeah, I was 29, so I had gotten off. Yes, that's it. That's it. Okay.
Yeah.
Good for now.
and head out. Okay. I think it's running fine. So I'm just gonna stop the YouTube live stream over lunch and restart it after.
Did you get all the talks for the second?
In there.
After lunch?
I haven't looked yet. We're working on, yeah.
Yeah, I only carefully reread the email last night and it was like, oh, I need to open everything the night before on a Sunday? Oh.
We're doing it this morning. So.
Mhm.
All right, I'll see you later.
Okay, thanks, Megan.
Yeah. I think that. Yeah.
To be honest, every single slide. Maybe it's just the font that I've chosen. It just doesn't exist. Just
Why PowerPoint do you do? Why you do it like this? PowerPoint intentionally doesn't play nice with the.
or you know, Macs are just like, how dare you use PowerPoint?
Right. Yeah, exactly.
Let's break everything for you. Okay.
24.
Oh.
Because
Hate
they,
to
like,
reveal it.
nothing is that bad, right? They would mostly be
Yeah.
okay. It's just untidy.
It's just after all of the effort making like really
Oh, of
nice
course, yeah.
polished slides then.
They can't possibly be it.
Oh well, that's a bonus slide that probably won't use anyway. So okay. Okay, there we go.
Save that real quick, so we've
Yes.
got it ready.
Okay. Command. Yes. Okay.
Okay,
Presume
great.
that's saved now.
Yep, that's correct.
Great. Thank you very much.
Yeah,
for
no,
letting me, let me do that.
it's worth doing.
It's way better than I just look at my shoulder.
Yeah, because again, why bother spending all that time doing it right?
Yes, yeah, and, well, and then let's see, a lot of.
And so, it just sounds like. Yeah, there are some. Anything that I might start buying to. I think it's.
Yeah. I mean, how about that, because you have a problem with this.
Yeah.
Um. And, yeah, anything else, just, and you can find me on time.
Sure, thanks.
So do we need like another computer up here so that people on Zoom can see that there's? Well, so that's the problem. So, so we can either, if people share their screen, we don't have. People do away from me. So because we're sharing with Zoom anyway, like they could go and pin the Symposium if they want, but on user live stream, there's right. All they'll see is that's true. And I think for all, last time I checked, 4 people in the live stream. Yeah, that's just how it's gonna happen. Yeah. But because I mean, we are open, we are recording. So if anyone's on the Zoom and they want to see the shared screen and the speaker, they can think about.
Okay, so okay, wait. If you want to move around, then you can use this.
It's
Oh, it's on. Okay. Like just make sense on. Okay.
You found that one. Big one's forward, little one's backwards, and this one you just gotta hold a second to make it fun.
Bluetooth, so it just takes a second to shine the backer. Okay.
Why is your live? Thanks for volunteering. That one's stupid. Do you want to present your note? Okay. Why are you subtyping? Stop subtyping.
It can be useful for people.
I suppose.
It's like an accessibility.
It doesn't bother me. Yeah. I give it to
It's not great subtitling, but it does. Hello, everybody. Welcome back. We're going to start our second session of talks. The subject of this is rocky exoplanets. My name is Sarah Moran. I am a new Sagan Fellow at NASA Goddard. And our first speaker is Maggie Thompson, who is currently at ETH Zurich, but also Carnegie EPL sort of at the same time. And I'm gonna hit the button there and I'll wave at you. So like you make eye contact with me to acknowledge your 2 minutes.
Awesome. Thank you so much, Sarah. I have to say before I get started, the last time I was in this room was for the 2010 astrodecadal announcement when I was a very baby scientist working at IPAC with Davey, who's in the audience here. So this is a very cool full circle moment for me. But I'm very happy to be here and to tell you all about the lab work that we've been doing in collaboration with folks at Carnegie and also at ETH to try to understand the interior atmospheric connection for rocky planets. Okay, so I'm going to split my talk today up into 3 parts. The first part, we'll think about what actually controls the mass and composition of rocky exoplanet atmospheres. And then once we have that understanding, I'll discuss our experiments to try to constrain volatile solubilities, how much of a particular volatile species you can dissolve into different melt materials, and also our outgassing experiments. And then with time permitting, I'll discuss how we can put all of these experimental results into our numerical models to help us actually interpret exoplanet atmospheric observations. Okay, so to start thinking about rocky exoplanets, of all the planets that we are currently trying to characterize with JWST, of the low mass rocky types, one of the types that's most amenable to near-term characterization are magma worlds. So these are rocky planets that have extensive lava or magma oceans at their surfaces, and they provide us with several observational advantages. First, they're on short orbital periods, and they also have bright dayside fluxes in infrared light. So these two plots here showing you radius and period, and also radius and mass, show you the distribution of rocky exoplanets that we know of, and in particular highlight some of these magma planets. You might recognize some that have been already started to be characterized by JWST, including 55P3b in particular. And so if we take a step back and think about how these rocky planets likely form their atmospheres, we can generally divide atmosphere formation into a few types. There's primary atmospheres, and these form by capturing hydrogen-rich gas from the stellar nebula. Then we have secondary atmospheres that form instead through outgassing from the planet's interior, either during planetary accretion or later through subsequent tectonic processes. And initially, it had been thought that most rocky planets are probably forming mainly secondary atmospheres, but it's actually possible, depending on the mass of these rocky planets as they're forming and their environment in the nebular disk, that you might actually instead have hybrid atmospheres that form through a combination of leftover primary atmospheres and also outgassing. And so if we're thinking about these magma worlds, those that are really hot, they have lava or magma oceans on their surfaces, what actually controls their atmospheric compositions? So of course, the rocky precursor material from which these planets form will have a dominant influence on what the atmospheres are composed of. But another important factor is how these major gas species, be it water vapor, carbon dioxide, how those gas species actually dissolve into the magma, into the molten silicate of the planet. And so we can understand this in terms of solubility. So this is often put into different laws, and these exist for various species. So you're basically relating the mole fraction or the amount of this dissolved species in the planet's molten interior to the partial pressure of that species in the planet's atmosphere. Whoop. Sorry. And one thing to note is that there's currently very limited experimental data on solubilities of major atmosphere-forming gas species for melt materials that are unlike just present Earth Day-like materials. And so that's what we're trying to fill with this gap. Okay, so there's a lot of different volatiles that we could focus on, but there's been some recent attention, in particular thinking about the earth science literature and going back to hydrogen. So it's been thought that as a planet is accreting, if it's massive enough, the planet may actually be able to hold on to some amount of primary atmosphere. And in a recent paper that came out last year by Ed Young and other folks at UCLA, they thought about whether you may actually be able to have Earth's water come from a primary atmosphere around the early Earth, and then chemical reactions between oxygen in the planet's magma ocean, the hydrogen that then dissolves in this molten magma ocean phase could provide you with a source to actually hold on to this hydrogen for significant amounts of time, and then you actually form your water. And so we wanted to help fill this gap even more by providing more experimental data on hydrogen solubility. Okay, and so here's our setup to perform these experiments. So this has all been done at ETH. This is a gas mixing furnace. So this allows you to heat materials up to 1600 degrees Celsius, and we can mix different proportions of carbon dioxide and hydrogen gas. This is done in the basement because you are using an entire tank of pure hydrogen gas, which is a bit dangerous, but thankfully no explosions have happened since I've been there. And so you create your silicate samples, you actually hold them by this cute little chandelier of material, you place it inside this furnace into the hot spot, and then you send a voltage through the system after you've let the samples and the gas equilibrate after some time, and then you quench it so you form this nice glass here. And then in these glasses is where we can measure how much hydrogen is actually dissolved into this material to give us our solubilities. And so I've done a series of experiments with a range of compositions. So I know for our astronomy folks, you might be thinking, this table means absolutely nothing to me. But all you need to know is that these are basically like iron-free basaltic materials. And we chose these because it's allowing us to measure the control of all of these different major elements, silicon, calcium, magnesium. And then we actually did a couple samples where we actually did introduce iron to see the effect that iron has had. We did a range of experiments under different hydrogen to CO2 gas ratios, so in the gas phase, including just pure hydrogen. I really did not enjoy those experiments. I got really nervous if there was going to be a leak that I would not be alive, and also a range of temperatures. And then after we have our quenched gases, this is the, we are going to be able to measure how much hydrogen has dissolved using a technique called Fourier transform infrared spectroscopy, or FTIR. And so this is what you're looking at here. So this is your infrared spectrum of the glass. And so from around 2 to 10 microns, you mainly see a bunch of silicate glass features, but the main feature that we care about is this small little peak, right? Just a short word of 3 microns that's due to hydroxide dissolution. And so that's the form that hydrogen is dissolving in all of these samples. Okay, and so in order to actually quantify how much hydrogen dissolves in these materials, we can apply this Beer-Lambert law, which basically allows you to relate the height of your OH peak to the amount of hydrogen that's dissolved. So if you can ask me questions about exactly how we calculate this later, what I will note and what is important is that in none of our samples, regardless of gas ratio, composition, we don't measure hydrogen dissolving as molecular H2, even though that's the form it was in the gas phase. If we were to see that, we would have seen a peak right around here, and we don't. Okay, so here's our main results from these experiments. So I'm showing you on the y-axis the dissolved concentration of hydrogen in parts per million as a function of the water partial pressure in the gas phase. Now, why water? Well, as I showed in the previous plot, the way hydrogen is dissolving is it's as OH, or hydroxide. And so as you allow there to be more oxygen in the gas phase, this actually helps your hydrogen dissolve. And so that's what you're seeing here, that as you have more water, which is kind of our way of quantifying how much oxygen is in the gas, you end up with more hydrogen that's dissolved. And so we're currently in the process of going through and seeing how does melt composition, for example, impact hydrogen dissolution. So this figure here is showing you, again, same thing on the y-axis, and then we have to figure out a way to sort of quantify the effect of our melt composition. And so one of the ways that we're looking at this is trying to use a few different parameters that can help us understand how interconnected your silicate network is. How much space is there? What's the porosity of your melt? Maybe there's more free spaces. So ionic porosity is the measure of the amount of free space between ions in your melt. Maybe if you have more of that, that allows there to be more room for your hydrogen to dissolve. And so that's basically what we're seeing here, is if you were to increase your ionic porosity, you allow for more hydrogen dissolution in the melt. But we're still figuring out exactly what all of this means. And in fact, some of it's a little bit counterintuitive to what we initially suspected, because there's different ways that you can actually characterize the amount of oxygen in your melt and how it's all interconnected. So stay tuned for more on this. And we also looked at the effect of temperature and the amount of iron in our gases, or in our silicate melts. So we are seeing a tentative increase with temperature, so hydrogen dissolution increases as you increase in temperature. We're not really seeing any clear dependence for iron in our glass. And in fact, what happens is quite interesting. Even if you add up to 30% iron into your sample, when it actually is heated and quenched under these conditions, most of your iron forms metal globules. Thank you. And so in the glass itself, there's very little iron. Okay, and so in my remaining 2 minutes, I will briefly touch on a new instrument that we're also using to measure solubilities and degassing speciation. So this is an aerodynamic laser levitation furnace coupled to an FTIR spectrometer. So this is the only instrument that exists like this in the world that's coupled with a FTIR spectrometer. And so this is why I'm very thankful to the Hubble community for allowing me to spend my time at ETH to work on this. And so over the last year, we've been developing this instrument that allows you to heat samples up to 2,500 degrees Celsius and even higher, and do this under a range of different background gas conditions and measure the spectra of these samples in situ. So I will show you a brief video of what this actually looks like in reality. So it's quite exciting. So you have a molten sphere of material that's a few millimeters in diameter. As it's being heated and levitating by this gas flow, you see gas being released. And then we have our spectrometer to allow us to do emission and transmission spectroscopy of these different materials. And this will provide a reference for helping to interpret these hot magma exoplanet observations. So just to show very briefly, here's some of our test results, where we're looking at the emission from our CO2 gas that's coming out of our sample nozzle. And so you can see the effects of temperature, and we're still in the phase of understanding our detection limits, but stay tuned for more. Okay, and in my last 20 seconds, briefly, I'll just say these experiments are all really great, but they're only as important as we can incorporate them into our models so that we can actually interpret exoplanet observations. So there's a great code that's been developed by Dan Bauer and myself at ETH that will allow us to compute chemical equilibrium conditions between a melt and the atmosphere interface. It includes things like solubilities, and also for sub-Neptune folks, real gas equations of state, which are important for these high pressure atmospheres. And so this plot I'm happy to come back to because I know I don't have time to go into all of it, but the point is that the volatiles that you see in your atmosphere are not necessarily representative of the interior. So you have to take into account solubilities for these sorts of rocky magma worlds. And I'll leave my take-home messages up and happily take questions.
For the experiment where you were like melting and levitating things, why don't you have to do that under vacuum or in a controlled chamber so it's not like atmospheric gas getting consistent?
That's a really great question. So that is a goal. Oh, sorry, I'll repeat the question. Why don't we do these laser levitation experiments under vacuum? Because we are doing this all open to the air. How do we deal with Earth's atmospheric contamination? So that is a goal, is to put this whole system under a box. It's actually, there's been simulations that have done, because these setups without the spectrometer do exist. And actually, when you float a gas around your sample, despite doing this in the open air, you don't end up with too much contamination from the Earth's atmosphere because of that pressure from the gas that's flowing around the sample. So we think it's okay. So even if we put it under a box, we'll probably still keep it at 1 bar, but flow something neutral like argon or something.
Ryan?
How does that model compare to other open source codes like Lavatos, Vaporov?
Yeah, that's a great question. So AppModeler, I would say one of the real advantages is it's super modular. And so if you want to be able to add in, say, a new, oh, sorry, should I repeat the question? Yeah. Okay, sorry. The question was, how does AppModeler compare to like LabAtmos or some of these other open source codes? So yeah, it's quite modular. You can add in new solubility laws super easily. One of the unique things is that it includes solubilities that are compositionally dependent, which is something that is really hard, I think, within our more the like astronomy frame of mind community. You know, we'll pick the salt hydrogen solubility law and a totally different like prototype one for CO2. This keeps it all very consistent. So if you pick the salt, all your solubility laws are consistent with that composition. And I believe these other codes are not including real gas equations of states. This is really important for your high pressure kilobar sub-Neptune atmospheres.
If we could have Jaren come up, you're right next to me, that's all. And one final question while that's happening.
Now, these are reports done at ETH, right? Because it's the only place in the world that has that capability, right? Now, thinking about as an Apple fellow moving towards the next chapter of your career, what have you thought about what did it take to you to come to the US and build that setup here in terms of money?
Great question. I mean, no, I think that would be awesome to do because there's just so much work that you can do with an instrument like this. It's a great question for how much it costs. I don't know. I've asked before. I mean, I think it's maybe like $500K or something like that. I mean, like the laser's quite expensive. I will also say an advantage to being at a place like Carnegie is I can do all sorts of stuff with carbon solubilities because they have a very similar, these gas mixing furnaces are quite kind of common from the experimental petrology side. So there's plenty to do on that front. But yeah, we can chat more because I think
so it's not more crazy within the startup budget of a faculty, let's say.
No, that's right.
Let's thank Maggie one more time. And then our next speaker is Jaren Ashcraft, who's currently at UC Santa Barbara, and I'll just hand it to you.
Thank you. Do you mind if I use this? Is that all right? Yeah. So hi everybody. Yeah, I'm Jaren Ashcraft. I wanted to open by saying aerodynamic laser levitation is like the coolest thing I've ever heard of. That's just a great name for science stuff.
The reason I'm using this is because I have a hand tremor, so you might see my hand shaking. That's normal, and I'll be careful around the coffee table so I don't spill things on you all. But today I'm going to be talking about something that's near and dear to my heart, and that's polarization and, well, high contrast imaging. To open, because I'm a new Hubble Fellow this year, I just wanted to tell you a little bit about where I'm from. So I'm a Hawaii-born optical engineer, and what that means is I'm kind of like an eye doctor for telescopes. So I was born and raised on the Big Island of Hawaii. Aloha kako, everybody. I'm about like 30 minutes down from the Keck HQ, if any of you have observed a Keck before in Waimea. But I did my bachelor's of science in optical engineering at the University of Rochester. It was cold. And then I really liked optics, so I did my PhD in optical sciences at the University of Arizona. It was hot. Since then, I just started 2 weeks ago at the University of California, Santa Barbara. It was medium hot cold. This is my research group, those who were there. We get a lot of ice cream. It's been very fun. And now onto the technical stuff. Let's talk about the intersection of polarization and high contrast imaging. So just to get on the same definition, because I know a couple of definitions for the word polarization personally. When I think of polarization, I think of the orientation of the electric field vector in light. And you'll see kind of polarization scientists swing their arms around kind of like this, describing the polarization state. So this is linear polarization. And in astronomy, you can do some really, really cool things with it. Here's an image taken by my soon-to-be PhD, Miles Lucas from the University of Hawaii at Manoa, doing some of the coolest astrophotography ever by looking at debris disks in polarized light. You see, starlight doesn't tend to be that polarized, but when starlight bounces off of things, it causes polarization to happen. So if you look at astrophysical targets in polarized light, you can see really, really cool photos like this one, and probably also do some cool science. Next thing we need to define to kind of set up this problem is high contrast imaging. So if you were to hop on the magic school bus and go drive to the planet you wanted to look at, you would see something on the left, no problem, right? Big planet, clear as day. But we're restrained to telescopes when we try to view these things, and what you actually see is something on the right. That core represents kind of the starlight, and all this stuff around it happens because light diffracts and spreads light all over the focal plane. And there is actually a planet on that photo. I don't know if any of you with really good high contrast eyeballs can see it. But typically, in order to actually resolve these signals, we use something called a coronagraph. Now, this is a technology that was borrowed from Bernard Liot, a solar physicist, that essentially just lets you punch out and filter this starlight. And the effect of using such a device is we have kind of the before scene on the left. If you don't use a coronagraph and just directly image, this is the kind of thing you see. And on the right, if you use a coronagraph, the exoplanet pops up plain as day. And so that's all very nice. Unfortunately, the sort of previous figure that I showed only works if your system is ideal. And regrettably, systems are never ideal. And so multiple sources of error can cause sort of light to spray across your focal plane when you're looking at the image of a chronographic instrument. And you'll get these things called speckle that on the left here look like these dots that are sort of showing up in the focal plane. However, something I'm interested in studying is the polarized aberration, or how polarization couples into light spreading on your focal plane. In this figure by John Christ, who actually just works up the hill at JPL, a really talented optical modeler, he determined that for the Habex chronograph, the telescope that this image was generated for, found that polarization aberrations actually predominantly arise at the inner working angle of the chronograph, or the minimum separation that these chronographs can see. So it really limits our ability to resolve exoplanets that are at small angular separations, not unlike an Earth with respect to a sun-like star. And unfortunately, in kind of pursuit of habitable worlds like observatories, this signal tends to be on the order of the brightness of, or the contrast of these exoplanets. So it's really something that we need to address. We have a lot of fun toys coming up for astronomy. These are kind of the 4 next generation telescopes that we're looking to develop technology and do awesome science for. The ground-based 30-meter telescopes, the ELT, GMT, and TMT, all have direct imaging as a science goal and employ these really curved mirrors in order to fit within an acceptable observatory volume. And that means that they're going to have polarization aberration.
Similarly, we've heard a lot about NASA's habitable worlds today, is going to experience the exact same problem, uses very curved mirrors in order to fit inside of a telescope so that you don't need to, launch a building, basically, although maybe you're already kind of doing that. So all of these things will, or we sort of expect them to be sensitive to this polarization aberration at small angular separations. And so in graduate school, I sort of asked this question: how do we model these polarization aberration effects? And this is the part where we turn into an ad. I wrote an open source software package and I called it Poke. There's no acronym, I just like this food. That's real, but if you go to the GitHub and look at the README, you can see the fish market that inspired this name. But the goal of Poke was basically to address this technology gap in the open source. And that's that we don't have ways of describing how the polarization state changes across a beam that propagates through a telescope. Because, I'm going to depart from the microphone a bit, you get these amplitude, these two columns on the left, and phase aberrations that change depending on where you are in the beam that propagates through a telescope. And that's what causes that degradation right at the inner working angle of your coronagraph. So, in collaboration with Sebastian Haffert, a former Hubble Fellow, who some of you probably have heard from already, and Dr. Rania Anche, we led a study trying to essentially be eye doctors for the ground-based kind of ELTs. And this plot on the right shows the peak degradation in contrast for the colors correspond to different telescopes as a function of wavelength, which is on the bottom axis there. And what we find is that this, something that was sort of known but hadn't been formally characterized for these telescopes, is that the peak contrast degradation is highly chromatic. And so if we're going to push to shorter wavelengths, this effect is going to be worse. Alternatively, if you do further infrared science, you're good. Don't worry about it. And so if we're going to push to shorter wavelengths, so this will become a dominant error term. In a paper that is currently in review in collaboration with some folks at JPL that we submitted to JADIS, I sort of replicated this study using Poke with respect to how the contrast degradation for different mirror coatings, denoted by the columns, these are just coating recipes, correspond to different degradations at the focal plane for different coronagraph architectures. And we see very much the same thing. Each of these is an image of a coronagraph's focal plane, and the degradation is concentrated near the inner working angle. But certain coatings don't experience the effect as badly. So I've been doing a lot of, in graduate school, basically telling everybody that, oh no, we have this problem, and now I have to make good on this promise of trying to fix it. And so that's kind of what's happening next. We have these wonderful open source packages to like the altruistic yield optimizer and exosims that allow us to directly trace images like this, focal plane intensities, to Earth-like exoplanet yield so that we can precisely understand how errors in optical systems translate to number of rocky exoplanets detected. And that's the immediate next step and the first thing I'm going to be doing as a NASA Hubble Fellow in collaboration with some wonderful people at Goddard and principally doing kind of the main work, but also a variety of collaborators from multiple institutions. And that will be kind of the first thrust of my research as a Hubble Fellow. However, in order, once we've kind of determined the relation of polarization to Earth-like exoplanet yield, we do also need to eventually validate these models in the laboratory. And so this is kind of the second main thrust of my research. I could, model these effects all day and then just call it good, or we could go and try and characterize them. So I made another open source software package named after food. This one's called Katsu. And the idea was, I also noticed kind of a technology gap in the open source for polarimeter data reduction and control in the laboratory. And, in order to help spread these techniques that are actually from outside of astronomical instrumentation to measure the polarization kind of transfer function of an instrument, we wanted to develop this open source software in order to rapidly construct these instruments. And this was done in concert with William Melby, who actually worked in this office. I found his old name tag down this hallway. He's an undergraduate at UCSB, Rebecca Zhang, who's a PhD student at UCSB, and Kenji Mohal, who is actually a software engineer that's between jobs at the moment and just wanted to contribute to an open source project. So this really kind of shows the power of doing things in an open source environment. And if any of you are looking for software engineers, please talk to him. And so using the grommet polarimeter, you can see the cartoon dog there on the left. It's the real name of this polarimeter. We measured the space coronagraph optical bench called SCOOB, which is a coronagraph that I built in early graduate school. And I was actually able to measure polarization aberrations of a coronagraph. Ideally, these instruments, this beam is basically looking at the pupil of the coronagraph or an image of the telescope mirror. And you want it to be completely uniform, and you'll notice it's not. Part of that is because the optics are dirty, but I want you to pay attention to kind of the mid-frequency aberrations, the red to blue oscillation of like 3 to 4 cycles per over the pupil. And this is an effect that actually doesn't arise from polarization modeling stuff that we've been doing before. And so I think it's indicative of coding inhomogeneity and anisotropy, which is also something that we don't really have models for, but want to pursue further. And so for my first 2 weeks as a NASA Hubble Fellow at UC Santa Barbara, I built a remotely operable kind of polarimeter testbed that we can use to kind of push the sensitivity of how we measure polarization state changes in optical instrumentation. And now I've been going a little fast because, I'm excited. So I wanted to play a little game with everybody. I've established kind of a silly naming convention. Does anyone want to guess what we named this polarimeter?
Sushi.
Sushi, that's a good one. This is actually me getting suggestions for future stuff. So we have sushi. Any other guesses? Well, what was it? Ramen is good. So what I've seen pineapple, like PY-napple as another one. Ramen's good. I heard one more. Spam. You get it. No, you get it. That warms my heart. No, so my graduate students named this one and they called it DERP. And so the reason for it is because the kind of polarimetry technique that I sort of brought into their laboratory was the dual rotating retarder Mueller polarimeter. And if you just try to pronounce that acronym, it's DERP. We realized this morning that the control software in Python could be called DERPy. And so we're very excited about that. But in parallel with this modeling effort, what I'm going to be doing is exploring kind of polarization-based phase retrieval, polarimetric digital holography, and concepts that we're working on for minimum covariance polarimetry. And all of this is basically just to go through this cycle of do your optical modeling, validate the optical models in lab, refine your design, and iterate until we're good enough. So mahalo, everybody. Thank you for listening.
It's a really wonderful picture. Mike in the back.
Yeah.
Great names, first of all.
I appreciate it. I spend 50% of my time coming up with names, and then the rest is just, whatever.
To trade off between the inner working angle and the wavelength of the polarization observations.
Yeah.
For Amcor system, you're in the infrared, so maybe you're okay with the aberrations, but then the planet's really close, so maybe inside the inner working angle.
Yeah.
So is there sort of like an ideal stellar type that polarization observations are like best at being?
Yeah, no.
Please repeat the question.
Yeah, absolutely. So I want to make sure I get this right. The question is there an ideal stellar type for kind of insensitivity to polarization aberrations? And this is sort of where I admit a little fault in my education. I don't know the different star types yet. But with respect to kind of the spirit of the question on the wavelength dependence, you actually find that because it's concentrated near the inner working angle, that's where the kind of, if you observe in the infrared, your planet's going to be much closer to that inner working angle. But if you observe in like the UV, it's much farther away. And so the planet moves away from the inner working angle as you go to shorter wavelengths. But the polarization aberrations are worse. And so what we've actually found, and there are some future work that we've kind of found through the HabWorlds modeling effort, is that the visible might actually be kind of a sweet spot. And that's very encouraging. So look out for that coming up in the next year.
Well, thank you.
Thank you very much.
Other questions?
So if you mentioned the coding homogeneities effect. Is it your hypothesis or you are sure is the case? I mean, neither open answers. Have you thought about contacting manufacturers that, because we are looking at different type of coatings, different wavelengths and so forth. So we're interested in to know if it is the homogeneity of the coating, is there a better coating that works
No, yeah, that's an excellent question. So folks online, the question was, is the kind of figure on this slide the hypothesis is if it's coding inhomogeneity, or is it for sure? Definitely in hypothesis regime. We haven't nailed down everything yet. But this is kind of a factor that the late Jim Breckenridge had kind of mentioned, this kind of concept of form birefringence. If you would deposit metals onto a surface, they'll form these little columnar structures that look like birefringent optics. And so we think that it's possible. I'd love to point you to the work of Dave Harrington at the National Solar Observatory, who has done like really rigorous, like full birefringent treatment characterization of different coatings from commercial vendors. And so he's someone that I was looking to collaborate with to try and understand the actual origin of this effect, because hey, solar physicists do really good work too. So thank you for the question.
Let's thank Jaron one more time.
Thank you, everybody.
And then our next speaker is online, so bear with us while we switch gears a little bit.